goals and way forward for the workshop. At that point, I will run away to give a lecture to my third-year students, while Professor Goswami will talk a little bit of mathematics with all of you. And then after that, there will be a group photo. We will probably take a group photo at the entrance so we can see NITEC's office in the background. And then there is lunch at the Nielsen Student Center. After lunch, from 2 to 3 or quarter past 3, again, I have to disappear, unfortunately, for a meeting. But the idea is for whoever is here, especially those who are from Stellenbosch University, and there will be more joining us later today, they will give you a Stellenbosch University campus tour. So you can understand what happens on campus, where is what, and you can easily navigate yourself for the coming days. And then at 3:30, we're going to begin presentations by yourselves, by the honor students from SMU. And that session will be from 3:30 to 6:30. So 3 hours are allocated for that. And the idea is that each presentation should be half an hour, including questions. So maybe you can make it between 15 and 20 minutes, and then 10 minutes for possible questions and discussion. So you shouldn't you shouldn't be nervous at all about your presentations. It's just for us to get to know each other. We will have more discussions in the following days as well. And then this will conclude today. So basically, as you can see, today is really about getting to know each other. That's the main goal of today. And then we'll begin with further steps next day, and I'll talk about next day's program tomorrow, not today. Let me now begin what I've planned to do in this introducing NITEC's mathematical structures focus area. Well, the first thing I would like to do before I actually talk about the focus area, first thing what I should do is to show you the website of NITEC.
Vice President of SID, originally from.
You will see some of the pictures here that you already received in your bags, including this wheel of disciplines underneath bags. The idea is that these disciplines, although they seem to form separate parts of the pie, they're not supposed to be isolated from each other. The idea of NITEC is for these disciplines to interact with each other. And in fact, the idea of the director of NITEC is for NITEC to be a pan-disciplinary institution, which is the term that you also see on the title of our workshop. So the title of our workshop, Pandisciplinary, our title actually comes from the idea of the director of NITEC. That's his vision for NITEC. But we'll talk a little bit more what that means in mathematics. That will be an interesting discussion on its own. The first thing you'll see on the website of NITEC is upcoming events. Like, for example, you will see that today at 2 o'clock, Dr. Elena Caviglia from Stellenbosch University, she will join us a bit later, is giving one of the lectures in her series on two-dimensional categories survival guide. We will unfortunately not join her lectures because they began in the beginning of the month, and we will not be able to follow much if we join in the middle. But just to tell you that these mini schools, as this one, is happening actually every month. So once you subscribe to NITEC, to the mailing list, you'll be able to join those mini schools the ones you'd like to join and attend them and learn something interesting from them. Another thing that you could explore on the website is this tab here. And you could go here to various other sections of the website, one of them being research. Click on research, and then if you click on focus areas, this is where you'll find the areas in which ITHEX puts its focus for the next 2 or 3 or maybe 5 years. Now you might wonder, how is this different? How is that different from the pie chart? It seemed like already here we had the disciplines, right? How is this different to the focus areas? Well, the idea is that each of these focus areas will be combining several disciplines from the pie. So these are the ingredients. You can think of this as the ingredients. And this is what we're cooking with the ingredients. Among these focus areas, you will see there are quantum technologies, Afrocentric solutions for disease control and healthcare. There is very interesting mathematics that can go into that, by the way. Decoding the universe, quantum gravity and quantum field, computational modeling of functional materials for driving sustainable innovation. You see, this is there's a lot of chemistry in there, but it's actually mathematical tools also used there to understand chemistry. Mathematical structures for foundations and innovation. This is us, the focus area that organizes this workshop. I will tell you a little bit more about this just now. Let me continue with the list. Elevating data analytics and machine learning in South Africa, advancing capacity and statistics and machine learning through focused and collaborative research initiatives. Machine learning, you've probably heard of this thing, right? It's a very useful thing. And so there's an entire focus area dedicated to machine learning, as you see here. Complexity in biological systems. E5, unraveling complexity in coupled earth, environmental, economic, ecological, and evolutionary systems. Another focus area which reads as if it's very, very biological indeed, and it is. But let me tell you that the coordinator of this focus area, Professor Kanku, is actually a professor who is based in the mathematics division of the Department of Mathematical Sciences here at Stellenbosch. So this is biology, but it's very, very, very mathematical biology. Driving innovation in finance for sustainable growth, pioneering solutions for emerging markets and energy transitions. This is a very successful focus area in mathematical finance, basically. It involves a community of mathematical finance experts in South Africa and also in other Southern African countries. Professor Messias Alpheus is the coordinator there. And then we have two more. A South African community of Earth system modeling platform, carbon climate modeling, education and innovation in support of regional climate development risk and opportunities. And finally, computational and theoretical gravity, astrophysics, and cosmology. So you can see there is a big diversity of topics. And if by the end of this workshop, you will feel, well, I came to a mathematical structures workshop, but actually I discovered that I'm really passionate about complexity in biology instead of sticking with the mathematical structures focus area. That's not a problem at all. Then we will connect you with Professor Kankui. And this applies to all the other focus areas. Of course, we selfishly, given that we're using all the funding for this workshop comes from our focus area, we selfishly would like you to stay with us. But if you'd like to move to another one, that's absolutely fine. In fact, it is even possible to combine. We do want at NIFEX these focus areas to interact with each other. And that could also be something very exciting, how that can happen. Right. At this point, I'm going to now move to discussing the mathematical structures for foundations and innovation focus area. But before I do that, are there perhaps any questions in general about NIFEX Yes.
Prof, you didn't say anything about those details. And then number two, how did the institutions like you see the mathematical arrays under Stellenbosch, and then the elevating data is under the Rest of Pretoria? How do those institutions get to pick that fund? What pushes Stellenbosch to say we want to have only this focus area?
So thank you very much for the question. Let me first answer the second one. These institutions are just affiliations of the coordinators. These institutions have nothing to do with the focus areas. So the mathematical structures focus area is across the board on the whole country or across NIFEX. There's nothing to do with Stellenbosch University. It's just that I, who currently serve as the coordinator, happen to be from Stellenbosch University. Now you might ask, okay, how are these people chosen? How do you become a coordinator? Exactly, yeah. So there was a call for NIFEX focus areas. 40 applications came in, and then these 40 applications were grouped into 10 focus areas by similarity, and then each group then decided who should be the coordinator in that group.
Who qualifies to be a coordinator?
Anyone.
Anyone, students?
Not the honor students, not yet. To be a coordinator, you need to be a scientist that has certain substantial scientific contribution. So you certainly qualify, Maggie. I qualify. Amartya qualifies. Anybody who is associate professor or up could potentially qualify. In fact, not. Sometimes you see even this person, for instance, Regina. He's not a professor, but still they're a coordinator. So if at any point you would like to, because I did forget and need to mention, but I didn't, I would talk about this now, but in fact for the mathematical structures focus area, we have a coordinator and a deputy coordinator, and Professor Maggie Aphane is deputy coordinator. But if at any time you'd like to take over and become the coordinator, then I'm happy to become deputy coordinator. So it's really voluntary work. It is a lot of work because you need to kind of do things. Okay, so any other question? And then your first question was, could you please remind me what your first question was?
No, my first question was, how do you become a coordinator?
Right, okay, I'll answer that. Okay, any other questions about the National Institute of Theoretical and Computational Sciences before we move on to talk about the specific focus area? Yes.
So I understand that there are affiliations with the universities concerning different areas. So I understand that there probably are going to be I have to
So focus area is not based anywhere. Focus areas are across the country. So you can join any focus area in wherever you are, as long as you are in one of these universities. And I think SMU should be here. Yeah. By the way, maybe I should also tell you that, so NIFEX has a very simple structure. So there is the director and the management team. The director is actually the only full-time employed scientist. Director gets salary as a director and as a scientist. The management team mostly are voluntary team, but most of them coordinate a whole node. A node is a collection of universities, and they, at some point they might get a bit of salary as well. Not quite a salary, but kind of a grant. But apart from that, like very high management team, we have associates. to become an associate of NITEX, you need to have or either already a PhD or maybe are working towards a PhD, but at the same time are already employed as a permanent academic staff. So the students cannot become associates of NITEX. The way you join the focus area is that you are supervised by an associate who is part of the focus area. So that's how students can benefit from focus areas, by being students of associates who are part of the focus area. And the exact benefit across different focus areas might be different. In some focus areas, they might say, we don't want to spend our money on honor students. We want to spend our money on master students. So each focus area kind of decides how they spend the funds. In our focus area, as you see, we have decided that we should definitely spend some part of these funds, even for honor students and even maybe for younger students, because we feel that from the goals of our focus area, we feel that this is an investment that will have a great return. Any other questions? Yes.
I heard you mention you guys have one focus on honor students and then young students. So if I'm doing my masters, do you consider it? Or?
Yes. No. Honors and up, but also honors and down. More honors and up, but if there are students in undergraduate level, for instance, who already are able to do a bit of research, then definitely we will also support them.
Like we did.
Yeah, we did, yeah. Any other questions about NITEX in general? Of course, I didn't tell you everything about NITEX. That if I tell you everything about NITEX, I should be talking for 3 hours maybe. It was just a quick overview. If no other questions about NITEX, then let me move on now to the discussion of our focus area. Let me reshare the screen. By the way, are there any questions from the online participants about NITEX in general? Seems like there are none. If you have any questions, please drop them in the chat and we will be noticing them as we go along, and we'll be answering your questions. This presentation is actually a presentation I gave last week at the inaugural function of NITEX. Okay, so let me first say a few words about the title. What does mathematical structures mean? Well, a mathematical structure is a formal framework in which you can look at certain kind of phenomena. This is a very general way of understanding what mathematical structure is. Have you encountered in your undergraduate studies something called a vector space? So a vector space is a mathematical structure. Have you encountered a topological space? That's a mathematical structure. Have you encountered a metric space? That's a mathematical structure. What other mathematical structures do you think you've encountered?
Space.
Inner product space. Fantastic. Yeah, that's a fantastic example. Any other example? Sorry? I can't hear. That one I don't know. Please teach me about it in the next.
Is a space.
Ket-Zero, I look forward to learning about Ket-Zero spaces. Will that be part of your presentation?
Yeah.
Okay, fantastic. I really look forward. Now, it says afterwards, it says for foundations and innovation. So you see, of course, everything in mathematics reduces to mathematical structures. So if we just left the title like that, if it was a focus area in mathematical structures, this would include all the other focus areas that I showed you, because in any science eventually uses mathematical structures. But what we are after in this focus area, what our focus is on, is the foundations. So it's about a bit more on the theoretical side. You know, we have this institute is called Theoretical and Computational Sciences. This is more about the theoretical side. But foundations doesn't mean that we want to be recycling the old stuff. We want to also develop new insights. So that's why where the innovation comes in. We really want to see novelty in exploring foundations in this focus area. And then there is a longer title, Uncovering Universal Theoretical Principles and Building Integrated Mathematical Capacity. You see, building mathematical capacity is where this workshop comes in, right? To foster South Africa's future scientific, technological, and economic progress. All right. The next few slides is going to be showing you who are some of the lead researchers in the focus area. So the way a focus area works is that it groups together large number of scientists. But the main work of the focus area is led by a few people. And so this large number of scientists kind of fall under leadership of the team. Hi, Elena and Luca. Hi. So these people who are leading the focus area are called lead researchers. The amount of lead researchers we have in the focus area depends on the amount of funding the focus area receives. Currently, all focus areas across WITS receive the same amount of funding. And actually, I can tell you what it is. So every year, currently, the plan is that every year, every focus area gets 650,000 rands. That number might increase. If we do well, the government might give more funding to WITS. And so we hope that that number will increase, but that's the current limitation we have. And so then that also limits how many lead researchers we can have, because each lead researcher will be making use of these resources, and since they're not infinite, then we have to limit that number. Okay, so this is Professor Goswami's page. Every lead researcher leads a certain project in the focus area. Professor Goswami leads a project called Analyzing Ideals. Have you encountered a mathematical structure called a ring? Okay. Ideals, actually, ideals don't come from rings. Ideals come from numbers, from number theory. But a very prominent female mathematician, Emmy Noether, transferred number theoretic ideas to abstract algebra, building on the work of Richard Dedekind. And after Emmy Noether's work, ideals became part of the central part of ring theory, but then they expanded even beyond ring theory. So they touch on many different mathematical structures, these things called ideals. And so the aim of this project is to look at all these connections across different mathematical disciplines where ideals come up as a useful tool. So that's the project that Professor Goswami leads. And you can see already that this project is already pandisciplinary in the sense of, if we think of each subdiscipline of mathematics as its own discipline, and in that sense, it's pandisciplinary. Because it brings in topology, it brings in algebra, it brings in functional analysis, it brings in category theory also, although Professor Goswami is only interested in category theory where he collaborates with me, not otherwise. Anyway, so that's one of the projects in the focus area. Another project is on point-free connectivity. And the project lead for this one is Dr. Simi Ratilal. You know what a topological space is, right? And you know that topological space or a metric space or a vector space, they're all made out of points. But in real life, where do you find them? Is there a point in real life? You put a marker on the wall. I'm not going to do it because I'm going to ruin this beautifully painted wall. But you put a marker on the wall, no matter how small your dot is, it's still not going to be a mathematical point. So the question is, do mathematical points even exist in the real world? Maybe they don't. But how do you do topology if points don't exist? The answer is point-free topology. And specifically, point-free connectivity is exploring a fundamental concept of topology, which is about things being connected. Like, for example, if you take a donut and you share it with your friend, you'll have to cut it in two. And then after you cut it in two, it will become disconnected. It's not connected anymore. But now, before you cut the donut, if you take a donut, it has a hole inside. And that hole is also sort of connectivity parameter. If the donut was like a muffin, that space has been kind of more connected than the donut, which has this hole in the middle. So these are the motivating ideas that lead to this subject of point-free connectivity, which also spans across several disciplines, including algebra, of course, topology, metric space theory comes in there. There are also some links with category theory there as well, and many other disciplines. Lattice theory, yeah. There are many mathematical structures that are needed for the study of point-free connectivity. Professor Eric Angentiana, he, by the way, is the head of department at Rhodes University of Mathematics. He leads a project on counting subgraphs. Have you encountered mathematical structures called graphs?
Yes, we have seen working on vertical graphs.
Fantastic. So that's what Eric is also interested in. And specifically, he's interested in counting subgraphs in a very broad sense. And the graphs he's interested in can come from any discipline. In fact, he's such a famous mathematician that he's even an editor of a journal about mathematical and computational chemistry. There's a journal called Match, which is a very important journal in combinatorics, in the study of graphs and other similar topics. He's one of the editors there. So that's the project that he leads under the focus area. Dr. Wenqi Ko studies reed spaces and its relation to stochastics. By the way, when I mention these people to you, each of them are not on their own. They have a whole group of mathematicians working with them. They're just leading each project. What is a reed space? You know what a vector space is. You put additional structure on your vector space. You make it more structured than it is currently. And that additional structure allows you to express some fundamental phenomenon that originates from stochastics. This is finance. Stochastics is linked with finance, right? Yes. Again, several different disciplines come in here. It's a very interesting topic for somebody who is very interested in mathematical analysis. There is also a lot of topology that goes on in here. This is me. I'm project lead for higher order structures across algebra, topology, and logic. And there is a certain language called category theory that allows you to identify patterns that are similar across disciplines. In this case, this project focuses on algebra, topology, and logic. So if you're interested in more abstract aspects of algebra, topology, and logic, then you might be interested in a project like this. I haven't mentioned some of the other names on these slides. You will see that there are certain postdocs. Do you know what a postdoc is? So postdoctoral, it's something you do after your PhD. When you finish your PhD, you become a professional mathematician, and then you're expected to teach. And teaching can take a lot of time. So to give a bit of time to do more research after your PhD before you start teaching as well, there is this notion of a postdoctoral. So it's something you do after your PhD. And we are very fortunate to have excellent postdocs in our focus area. Elena Caviglia is sitting right there. Luca Mesiti is also sitting right there. Kishan Dayaram is sitting right here. By the way, congratulations to Kishan, who recently got a job offer from University of Johannesburg. I hope it's not a secret anymore. Okay. So, in fact, Kishan will be moving to Johannesburg, at the University of Johannesburg, joining Professor Goswami, and he will be also available as a potential supervisor for master projects. And then we have other postdocs as well. Ranjita Ravi Prakash at UKZN, who works with Dr. Srinivas and Dr. Anna Laura Zauras, who's affiliated with UWC, University of Western Cape. Yes.
I don't know if this is an appropriate question, but does NITHEX thing that you talk about, NITHEX, is now NITHEX also funding postdocs, or is that not an activity associated with NITHEX?
The postdocs are not getting their postdoctoral fellowship from the focus area. They are postdocs outside of, the funding comes outside of the focus area, but they work with researchers in the focus area. So their work contributes to the focus area.
So NITHEX doesn't fund postdocs?
NITHEX does fund postdocs, but not through focus areas.
Independently?
Through the research, through the universities. Every university, or sorry, every hub, a hub is a collection of universities. Every hub receives a certain number of postdoc positions from NITHEX that NITHEX funds. And I think, if I'm not mistaken, Elena, do you have NITHEX postdoc?
Kishan is what?
Elena and Kishan have NITHEX postdoc. Luca has Stellenbosch University postdoc.
Oh.
And the other colleagues that I showed you, Ranjitha and Anna, I do not think they have NITHEX postdocs. I think they have local university postdocs.
Or NRF?
Or NRF, yeah. Okay, so this brings me to the final slide, which shows some of the other researchers that are not yet, at least, lead researchers. So let me begin from the bottom. So you will see there that it's written co-researcher. But what does that mean? Remember, I told you that the focus areas were formed like this. There was an open call. People applied. 40 applications came in. Then they were grouped into 10 focus areas. These individuals, Dr. Partha, Professor Brink, Professor Situti Moshoko, these individuals were among the others who are lead researchers that I showed you. We together, each of us submitted applications for a focus area. We were grouped together. And then in this grouping, for various reasons, including the number of people working under a person, Professor Moshoko, Professor Van der Merwe, and Dr. Ghosh are not lead researchers yet, but the others are. At any time, we might decide to either swap, or we might decide, if there is more funding, for them to also become lead researchers. So these are kind of the core researchers. They are supposed to be the leaders of the focus area in a broader sense. And then, very recently, when I met Professor Aphane, we invited her to join our focus area as a deputy coordinator. And so there is Professor Aphane. And I'm hoping that very soon also you will become a lead researcher, maybe a coordinator. So we'll see how that develops. The diagram there shows you the structure. So this is where I am, the overall coordinator. I make the decisions about the focus area, but I cannot make any decisions without approval of scientific chair, which is Professor Goswami. So he needs to approve every single, especially if it deals with finances. He needs to approve every single decision, and he doesn't. He only approves 10% of my decision. But actually, what is really nice is that we actually brainstorm the ideas, and then we develop together a solution that really is much better than the original idea, and that's how we work together. The core researchers, they influence the decisions. They're able to give their feedback, say what they think about it, and so on. The deputy coordinator helps the overall coordinator. For instance, for organizing this workshop, it wasn't just me, it was actually Professor Aphane, myself, and Professor Goswami, who put our efforts in organizing the workshop. Sorry, let me go back here. And then lead researchers also directly, if a lead researcher needs some resources to do something in their research, they will tell me about it. So if, for instance, you next year, you're a master student and you're working under one of the lead researchers, right? Lead researcher will say, my master student wants to visit a collaborator in another university. Can we maybe find funding for it? So lead researcher will tell me about that. And I will say, okay, this sounds like a good idea. Let me think about it. If I'm happy with it, then I will tell scientific chair, look, this is a really very good master student. It will be really productive for this master student to visit that collaborator. Can we maybe approve this? And then the scientific chair will say, well, it doesn't make sense to visit just for 2 days. It's not going to be impactful. If they want to visit, rather we spend a bit more money, let them visit for 2 weeks. Then I go back to the researcher and say, unfortunately, I can't approve the 2-day visit wasn't approved, but if you're happy with the 2-week visit, then we can approve it. So that's kind of how we work. And with the deputy coordinator, we just started now, so we'll see how that will develop. But your task is kind of to get input from all the associates. So I will be getting issues only directly from lead researchers and somehow deputy coordinator versus everybody else. Yes.
I'm still somewhat confused about the difference between a core and a lead researcher.
Core researcher is someone who should have been a lead researcher, but because of lack of funds, they're not yet.
In other words, they're part of the research group, but they don't have access to the funds.
No, they have access to the funds, but a bit less than the lead researchers. And also they have a bit less responsibility. The lead researchers each lead a project. And there is some understanding that every project will make use of some resources financially. Now, these projects are not isolated projects. They can involve various other core researchers as well. But the core researchers that are not lead researchers do not lead a project.
Oh, okay. So I think that's a technical difference. Yeah. They don't lead a project.
Yeah, they don't lead an official focus area project. Of course, they do a lot of research in their own right. But at any time, if any one of them says, actually, I have a lot to contribute to the focus area, maybe this year, let me be the lead researcher and let somebody else step down, we will definitely consider that. And also, if there's somebody else, like for instance, yourself, Professor Karen, we're very honored for you to be here. Thank you very much for joining us. If you would like to join as a lead researcher, we will be very happy to see how we can make that happen.
I must just warn everybody that actually this person has not taken me seriously. Shit. I'm just joking. No, I'm saying you haven't taken me seriously. I'm still not a member, I think.
You're still not what, sorry?
Associate or whatever it is that you...
Well, you see, to become an associate, you need to first want to become one. Then you need to be proactive about becoming one.
Okay, no, we'll check. Sorry, people, it's just me.
May I just add on these projects?
Yes.
For each of the lead researchers has a project, and this project is very wide in some sense that it connects people from not only exactly with whom you are already collaborating, but outside of your collaboration, but still connected with your projects. So why some people are core and not yet, because still they may not have that kind of broader projects. So the moment someone has, of course, automatically it can be so.
So the focus area was proposed by a certain group of people, and these are the core researchers. We don't want to take away kind of their foundational role in that. So that's why also we're not calling you, Maggie, a core researcher because you were not part of that initial group. But the focus area is not supposed to benefit only the core researchers, it's supposed to benefit the big community. So if somebody is very active in the focus area and wants to contribute, we will definitely find ways for them to do so. And maybe at some point we might actually decide to relook at the list of core researchers. I mean, we don't want to do it every 2 months, but maybe next year we will be relooking at that. Anyway, so this is where we are now.
And nothing is permanent. It's not that if Zurab is coordinator, I am scientific, it's that forever, not like that. It's very, very flexible.
Yeah, actually, I would, to be honest, I would love if very soon somebody else takes over as coordinator because it has been a lot of work for me to coordinate. I told you that we have these additional words, foundations and innovation, to make mathematical structures a bit more focused. But even with those words, this is still quite broad. So there is another parameter that makes it even more focused. This focus area is about doing research which primarily establishes mathematical certainty. So it's about building proofs. Any other mathematics whose main purpose is not to build proofs will easily fit in all the other focus areas. So if you want to do mathematical biology and you want to contribute to this focus area, then this should involve building proofs.
So the other focus areas will have similar structure, core, lead,
No.
or is it just
No.
this was a
No.
local decision?
This is our structure, our local structure, and the director has asked me a few times for us to tell the director exactly what the structure is so that others could possibly also copy, because I don't think that there is such a sophisticated structure in other focus areas as it is in ours.
Okay.
So the whole spirit of NITEX is a kind of, we're building it from the ground. Anybody who wants to build is most welcome to join, and we all shape what NITEX is going to be in the next 2 years. That's the spirit. So there is no like hierarchy. I mean, there is hierarchy, but it's just for efficiency of implementing things. But it's not like I decide something and then everybody should follow. That's not like that. We are building everything from the ground. So that's why also the students are most welcome to join in this building process. So I said about building proofs. Now, in the area of building proofs, sorry, I don't know why that text shouldn't be there. In the area of building proofs, one starts to distinguish between what is called high quality mathematics, and I'm putting in quotation marks because it's impossible to define what is high quality, and less high quality and less high quality, and so on. Imagine you discovered a new mathematical fact, a new theorem, and you wrote down its proof. Now, your theorem requires 2 lemmas to prove the theorem, and then it has an application in physics. And now you decide, okay, I have 2 lemmas, I have my main theorem and my main application. Let me write 4 papers. The first paper is going to be about the first lemma. The second paper is going to be about the second lemma. The third paper is going to be about the theorem. The fourth paper is going to be about application. You can do that. That's possible to do it. But then each of your papers become what mathematicians sometimes call low quality. Whereas if you put them together, if you didn't split them up, if you put them together, the whole thing would be in its own higher quality. And there are some journals that have a reputation of being high quality, and there are some journals that have a reputation of being less high quality, and so on. So quality in our focus area is very important. And here what you will find is a list of journals in which every core researcher has published at least 2 papers. And the thing in brackets, when it says Q1 or Q2, that refers to a classification. If you take all papers in mathematics and you divide it into 4 sections, 4 quarters, Q1 refers to the top quarter, Q2 refers to the second quarter, Q3 is the third quarter, and Q4 is the fourth quarter. What we strive in this focus area is for us to write our papers, our research outputs in such a way that we improve the quality of journals in which we publish. So preferably you stay between Q1 and Q2. And then another thing that matters is engagement. Networking is very important. Something else that our focus area contributed to funding was this very historic meeting between the London Mathematical Society, South African Mathematical Society, South African Mathematical Sciences Association, where, by the way, Professor Aphane gave one of the significant talks on the first day, and for the whole of the workshop, we will talk about her talk. It was really a remarkable talk. The talk was about you. It was about SMU, and it was a very impressive talk. And one of the outcomes of this meeting was that we decided that for PhD students, and this is you doing PhD after you finish your master's, we will have a program where we have a co-supervisor from UK, and we will have funding for you to visit that co-supervisor once every year in UK for 3 months. This is fantastic. Imagine being enrolled in a PhD program in South Africa where every year for 3 months you can visit your co-supervisor in UK, and everything is all the funding is covered. You don't have to pay anything for it. So this was one of the great outcomes of this meeting. There were also other great plans we made together. You will see here, this is the president of the London Mathematical Society. This is myself. This is Professor Maggie, as you can recognize, Professor Sikelela Notununu. By the way, do they know about Professor Notununu?
I don't know if they know. You can tell them.
Professor Notununu was PhD supervisor of Professor Aphane.
And the masters.
And the masters. He is an incredible mathematician, very humble, but amazing, both as a person and as a mathematician. He served recently as the vice president of the South African Mathematical Society, and now he is currently the executive director of the South African Mathematics Foundation. It's the same person as he's also head of the department at Fatlane University of Technology. By the way, let me tell you a little bit more. So Professor Notununu studies the different kinds of mathematical structures, including metric spaces and topological spaces. Professor Brink van der Merwe studies mathematical structures that are related to computer science. So if any of you at some point will become interested in computation and computer science, there is a lot of interaction we have with him about that. And Professor Ghosh is interested in topology and category theory.
Prof, before you move on, you've indicated that the 4 PhD will be sponsored to be visited the UK if there is a collaborator.
Yeah.
By who?
So the three societies together will try to identify funding for that. Professor Loiso Nonga is also helping us. There might be some contribution that IMSA can make, the new institute that's being established at WITS. It's actually already established. So the funding still needs to be raised.
There will be a call.
And then there will be a call, of course. Yeah, this is in the process of being established, but the decision was made that we really want to go for this project. And the last slide, on the last slide, last week, I showed them the slide for our workshop. I changed the picture since then because at some point there was a plan to go to this place, but the plans changed. We can still go there if we have enough cars. And then this document is the story of our focus area, which we'll be publishing from next year onwards and updating it as we go along. At this stage, I'm done with the presentation of the focus area. I think it's already 11 o'clock, so I'm right on time. But if you have a question or two still, please do ask. Oh, no, I'm not right on time. I completely miscalculated everything. This was supposed to be 20 minutes. And I forgot about that. I'm sorry, I talked for much longer than I should have.
No, they needed that information.
Yeah,
They needed
yeah.
information.
Now we have to disappear for the lecture.
Yes, I have to disappear for my lecture. I think it will be nice to have a little bit of a break. And then you could continue on with, maybe it's better we come back to goals the way forward when I come back.
Yeah.
And you can engage with a bit of mathematics during my lecture.
We have a 5 piece break and then we will listen.
Yeah.
Yeah.
Yes.
Just wanted to ask someone consider what you were the slides you presented.
Yes, I've shared it on the chat, and I'm also going to share it on our WhatsApp group. I shared it on the Zoom chat. We're going to share on our WhatsApp group. What's that?
It's out.
It is another one, right?
Where do you want?
Yeah, it's outside.
There's one there. There's one here.
That's what, yeah, I'm feeling about the 5 minutes. How are you? I'm feeling about the 5 minutes.
I think we can continue. We can continue.
How are you doing? Wait, well, if you have some suggestions about what to change in the program. Did I edit the program? Yes, I edit you to the.
कैसे हैं?
ठीक है आप
एकदम बिंदास है।
हमारे दोस्त है अली मकान से हैं You just tell him what's been
बिरयानी ले आए हैं आपके लिए?
बिरयानी भाई तो एक दो बार बना के
बीवी भी साथ है ना तो बनाते हैं
ओ, नहीं तो एकदम बाहर कर दीजिए।
दुकान पर लात मार के निकालूंगा
Coming from Pakistan and no biryani is impossible.
It's impossible. So I told you about him, UJ.
Yeah.
He's very prolific.
मुझे तो पास था वहाँ पे
Mujahid Abass. ये उनके SMS में थे.
Ah, yes. He also works on someone in my department, X1 theory.
Oh yes, on my PhD thesis. His signature is on my PhD thesis because he was the director of general when I defended my PhD.
So you worked on Lee symmetries.
He's better.
Your PhD was.
Yeah, he's my co-supervisor.
Well, quite a super performance.
मैंने विट्स यूनिवर्सिटी में कोई दो बार चक्कर लगाए थे.
Now you are doing postdoc here. Stellenbosch.
Yeah.
And who is your host?
I'm working with Shibu,
Okay.
but my official home is petrol landing. Biological petrol landing.
More in the, he's in the applied net.
He's in the he's working in this focus area of biomathematics and Gangway.
Gangway.
He is a supervisor.
He was his supervisor. So he works on
Dynamical system.
works on dynamical systems.
Currently PDs and the dynamical system.
Applications or theory? It's convenient because
Yeah, when you're on the other side, it's a problem.
imagine you are alone here.
Building, you need the car.
Yeah.
Except if you take the stairs, then maybe works.
Yes, so, but if you come through stairs, then you don't need tap. Lift, then you need tap.
Just the member of SAMS.
Ah, you paid.
No, I think institute paid.
Ah, fantastic.
People organize.
Yeah, yeah. Because,
Organize that.
The deputy president.
we had a long email conversation with Sivu that pay for the whole department, then it's much convenient.
Yes, exactly. But currently they're processing my
Yeah,
fee for the 2 years.
don't worry, it will happen very soon because Winch is very, very efficient.
Vinci. So no, they already submitted the invoice to us, so it will be processed soon.
Yeah.
Very soon. And professorship also means told me to submit abstract, and I already submit for the Congress.
Ah, yes, yes. Because there will be a special session on Lee symmetries as always.
Yeah.
Is you.
Masood again.
I thought you. Everybody is lying about symmetry. You are only doing Lee symmetry, right?
Yeah, but I think Masood is running that thing. He always does.
But why you are not part of the organization?
I'm not important.
You are now really lying symmetrical.
No, he don't know his importance.
No, he's the only person in South Africa, works in Lee symmetry, does know the definition of a Lie group. The other people don't know what is a manifold. I'm not joking.
He don't know his importance.
Yeah, I will teach him.
Baba Ali Symmetry.
Really like my,
No, Marcus, and you can some of them wants the department, that we have planned. Yeah, you.
Does it work? Yeah, no, that is fine.
Sure, I can.
So did you come from Gordon Bay now?
After them, after the
I
party.
took them to Pettit Bay.
Pettit Bay.
Just to see.
You like?
Oh, yeah.
Yes.
Twins, yeah.
Bringing, but I
On the way back,
Wait.
we stopped at the beach. in Spain.
Why?
He went for the first time in his life in seawater.
In water.
He was just.
Enjoyed a lot, yeah.
You see, wait.
I'll start with you.
No.
Ah, okay.
So they live in Gordon's Bay.
Let
We went, remember we passed train in the Gordon's
Yes,
Bay,
exactly.
then the beautiful road that goes.
But you are staying too far.
But maybe we. Kishan is. You are the one we're thinking of.
It's fast.
But now
It's beautiful, but it's,
because
you're not getting strain. Strain is not bad.
we tried, but it was really difficult because it was April, so not the right time.
Maybe in December you find a suitable place.
centrally.
Suitable place here. In December, maybe you find some.
And just continue it.
No, but we are thinking of, because Kishan is moving, taking.
Oh, then you can take over his place. So he's in, oh, he's there where Zurab is.
Yeah, so we are thinking,
Oh, what a good idea.
Yeah, that's a good idea.
Go in November or something.
I think, yeah.
Oh, nice, yeah.
That's a good idea. Saves you all the trouble. So,
He has election.
like, is it our time?
No. We will submit it anyway.
Yeah.
We'll say we reviewed it.
Yeah, and of course, we're doing the conservation law.
We also added the medical department
We are.
and the conserved quantities.
We can cite the paper.
Yeah.
Just so that they don't feel too,
But yeah,
Before we go for lunch. Oh, yeah.
where is Zurab?
He went to his.
I'm going to speak to him about something later. He's coming back, right?
Yes, yes.
Sorry.
And then
I think we can. So anyway, so the law is fine. I'm just gonna read the bio of Prof. Amartya Goswami.
yeah, the mark is the whole book, so.
Is it? So I don't need to.
You don't, if you want to say.
No, I don't have, okay. Thank you very much, welcome. Yes. I'm the young man from Zimbabwe Management Science University. I'm not sure if people are aware of but it used to be called the WITS, Medical University of South Africa. And then it was called the University of Limpopo. Now it's called the Zimbabwe Management Science University. So for now, I'm going to read to you the profile of Professor Amartya Goswami. But before I do that one, I just want to inform you that this is one of the unique professors who knows about the HDIs, and he has worked at the HDIs institutions and also the privileged university. So when you talk about SMU, he understands what we are going through. And then when you talk about privileged WITS UJ, he knows that one. So Prof. Goswami is affiliated with both the Department of Mathematics and Applied Mathematics at University of Johannesburg and also NITEX, the ones that brought us here. He's current research interest in associated and algebra, general topology, order, lattice and order algebraic structure. He has authored, I think it's more than 33, Prof. Here you have written 33 is more, a reviewed article, and he has delivered about 42 talks at national and international conferences, seminar and workshop. Since 2016, he has co-organized special sessions on category, algebra, topology, and logic at the South African Mathematical Society, that is SAMS, annual congress. And as of this year, he holds a position of vice president of SAMS. Okay, and he is currently under NIFEX, and he has more than 16 years of teaching experience, undergraduate to postgraduate level at various institutions. Let's welcome Professor Goswami. Thank you.
Okay, so all of you have to turn a little bit on this side because the board is in this side. We have roughly 1 hour. So as Professor Janelidze mentioned about this specific focus area is about such a mathematical structures. So this is all about mathematical structures. So that is one of the reasons why Zurab asked me just to tell you something very basic of this mathematical structure. So I will not assume you know any mathematics. Okay. So you can forget whatever you learned in your life and we talk together. It's not that I'm lecturing you. I never lecture whenever I'm teaching. In my whole life, I never lecture because I don't believe in lecture because lecture only politicians give. It should be interactive. I will tell, you will say that kind of things. Okay. So Zurab very roughly mentioned about this mathematical structure. So if we ask what is mathematics, of course we cannot have a definition like what is physics, what is music, we cannot say. But what we do in mathematics, that we can say. So if we see globally mathematics, then in mathematics what we do is study mathematical structures and the interactions between mathematical structures. So any kind of computation, whether you do it by hand or do it by software, the whole idea is to understand some structure, to understand the connections, to solve problems in one structure, you use another structures. And that's why how various different disciplines actually landed. So let's start with absolutely zero level. So, so when we don't have any structures or almost bare things, then we have sets. Just like that. And of course, sets is some mathematical structure. Anything, what you do in mathematics, almost everything can be expressed by sets. If we don't do that, that means we do not understand. Everything, whether the functions, everything what we study in some sense actually structures from that. So this is the bare thing where there is nothing. And once we have some sets, then we wanted to put some structure. So what is the minimum thing we can do? We can define a function. Do all of you know what is a function? Anybody here who never heard of function? Please don't feel sorry or guilty that, oh, I don't know function, I am doing honors. Don't feel like that. It's not that it may have missed. I mean, or maybe you have a misconception about function. Absolutely fine. But if you hide, then it will be a problem because then it will be a virus which will be infected. Okay. So at this moment, anything, whatever I'm going to say, if you do not know, raise your hand, I don't know that. Nothing shame about that. How trivial it is doesn't matter. Okay. So what is a function? To define a function, we need sets. Okay, how many sets we need to define a function? 2 sets, right? Minimum 2. Okay, very good. So let's take, we have 2 sets and we generally write like this way. And we have like this way, sometimes we write like this way. Okay, but what is this? It is a very special type of relation. Do all of you know what is a relation? Relation. You know. So what is a relation? So you take any set A, take the Cartesian product. You know what is the Cartesian product? You take the order P. So first element comes from the first set, second element comes from the second set. Okay. So if you take any subset from this, then that's your relation. Just any set. It can be the whole A cross B. It can be only one point, doesn't matter. So function is a special type of relation. That means we already mentioned that we need 2 sets and some pairing will happen. But relation can be any pair as long as the first comes from first, second comes from the second. There is no problem. But to become a relation, become a function, there are some conditions need to be imposed. And do you remember those conditions? What is the definition of a function? Anybody? What kind of things will happen on R such that R will qualify to be called a function? What kind of pairs I'm allowed to choose? Yes. Try. It could be maximum wrong. You will not lose any money. Absolutely fine. Tell me.
I want to know which function are we talking about?
I'm talking about any function, the definition of a function. Any function, all functions. Any functions will have the same definition. What kind of pairs we will take? Is it clear that A cross B will contain like this, right? The first one will come from first, and the second one will come from the second.
And
But R to be a function, this pair need to be chosen in a very special way. Only some very specific people should be there. What are the conditions need to be put such that these will qualify to become this person? Yeah.
So for R to be a subset, right, it means,
R is already a subset of A cross B.
so I'm just trying to.
Yes. Sure.
So in order for it to be a
Function.
function, yes, it would mean it has to have the properties of A and B.
But A is always come from A, B is always come from B. That's already in the relation.
Of course, we maybe not two elements in B
Yeah,
should come from the same element from A.
good. So we cannot have this kind of picture. So if A is here and we have B1, B2, this is not allowed. So we cannot take pair like this. We cannot put them in my relation. This is not allowed. Okay. Anything else? Anything else?
If I say the infimum of A and B.
Infimum? What do you mean by infimum? We have just sets. There is no distance here. We are not in a metric space. We are just set. 1, 2, 3, 4, right? There is no distance. What else should be conditioned so that we have secured that it's a function?
There's a comment. Sorry. I think someone.
Each has at least one B. Yes, that's already covered, right?
Not really. I think that's a good.
Each A, sorry, I did it. Yeah, each A has at least one B, yes. So that's the second condition. So every element of your this set A, which appears in the first place, must be associated with someone. So let's draw intuitive picture. So if it is your A and this is your B, imagine we have 4 elements, we have 3 elements, we associate with this. And of course, we cannot do this as already mentioned. This can go this place, that's allowed, right? 2 people can go to the same place, but 1 person cannot go. So when I teach this in undergraduate level, I say, this is a function, this is not a function. Always do this exercise 5 times, your hands will be good, and also you'll never forget it. This is not a function. Okay, so like this, but this can be a function. When you practice it, then you will never forget it. Okay? So then this can go here, but I cannot left anybody untouched here. This is not allowed. Everybody must be associated with something. And when I put that condition with this, then said everybody has uniquely go there. Why uniquely? Because these forces it need to be there. Okay? Good. So a relation having these 2 properties together, and we said for every element here, there exists a unique element here such that the pair is in my relation. So that's the function. And this is the only definition of function. When you open this calculus book, they may say it's a machine, you put something here. There is no machine. There is nothing about real world. Mathematics don't exist in the real world. Believe me, mathematics don't exist in the real world. Only exist here. Okay, you are shocked, right? Yes. This is not a one pen. This is a realization of the notion of one, which only exists here. Because if this is one, then what is this? This is also one, right? No. Let me ask you a very simple question. Can you draw a tree? Can you draw a tree? Not very a nice one. Can you draw a tree? Can you? All of you are lying.
What do you mean?
Yes, what do you mean? Of course, you should ask this. What do you mean? You can't draw a tree. You can draw a picture of a tree. Try to understand the difference. You can't draw a tree. You can draw a picture of a tree. Picture is the realization of something real. 1, 2, 3, 4 addition, your metric space, vector space, functional analysis, Banach's theorem, everything can be maximum says a realization. I mean, you can go for the applications as realizations of those concepts, but those concepts as it is, like points, sets, none of them exist in the real world. As Zurab was saying, where is the point? You can't actually tell where is the point. I cannot say it's a point. You can say, okay, there's almost approximate realizations of something. So everything what we do this, and this is the amazing power of mathematics. It 100% don't exist in the real world, but if you remove mathematics from the real world, whole world will collapse in 1 second, even less than 1 second. Everything, like this computer, as you know, it's on the Boolean algebra, which is 0 and 1, which don't exist in the real world, but if you remove the 0 Boolean algebra, everything shut down immediately. So this is the difference between mathematics and applications of mathematics. These two are very different in nature. Application of mathematics, applied mathematics don't exist without mathematics. This is an absolutely dangerous misconception. Even some staffs tell students you can bypass mathematics and do applied mathematics. Believe me, they are lying. My own PhD is not in category theory, it's in mathematical biology. So I know applied mathematics, and then I shifted to pure math. So if you really wanted to do applications of mathematics, you really have to learn mathematics. You cannot do applications of mathematics and applied mathematics without knowing any mathematics, then it's a fake. Everything will become a toy model, nothing will be applied in the real world. Of course, you will write your papers, you will get a promotion, but no, you really need to know mathematics. Okay, so we have a function. So once we have a function, then we can actually tell a special type of function to start our structure, and that's called operation. So if we have, say, a set A, take the Cartesian product with it, and then take the set. So now it's just a function where this, by the way, when you say function, these two people, A and B, have their special names. Do you remember that? What A is called? Domain. And B? Codomain. Who is range? Who is range? Huh? B is codomain, you said, I agree. Then who is range?
In the
No, but then why can you have two names?
Yeah, I think the range is bigger. In the
Is range bigger than codomain, smaller than codomain, maybe it's the same, or it don't exist, I'm lying.
smaller. Yes, not smaller, it's inside the, in the, supposed to be in the codomain.
Is in the codomain or it can be full?
Range is smaller. They are just the elements in the domain that are being mapped.
Right. So what is called range? So this is domain. And this is codomain. So if I wanted to write mathematically range, how should I write?
A subset of A.
Subset of B. Here. So generally we write like this way. Exactly what you said. So this means everybody who is associated with somebody, because we said we have an obligation to associate everybody in the domain, but we have no obligation to associate everybody on the other side. If we make also that conditions, then this whole thing will become equal to B. And what kind of function is that? Huh?
When
Projection.
Onto or surjection. So this animal is called image of this function or range. Okay, good. So if we have a function where your domain is a Cartesian product of a set with itself and your codomain is the same set, then that type of function is called binary operation. Okay, why binary? Because in the domain you have two sets. So if I have only one function from A to A, so this is called binary. So what should we call this one? Just by English. Unary. Okay. Can you go down? So pi means, I mean, we can write it like a square, right? Not squaring in a real number sense, but just a notation, right? This one we can write like this. What will happen if you go down?
Here it's empty. The identity function of.
No, identity function can be here or not necessary, right? And I'm saying I'm reducing the power. That means first I take 2, I could say 3, 4, 5, right? And then I'm decreasing my number. So this one is agreed, it's called binary because of 2, it's called unary because there is only one set here. Now we wanted to go one more down. And that will be a singleton set. So we take a singleton set, just put any element there, and we take this. Believe me or not, you know this before you learn mathematics. Can you give me an example of this? And this is called nullary operation. You have seen this. Since you started learning university mathematics, you have seen this. Not in a fancy way like this, but in a different way. You can't start your calculus without knowing this. Yep. Yeah, null means 0. So that's why it's called 0. Okay, so I'm giving a hint and then you tell me how. If we wanted to say an element X in a set A, how we write? X belongs to A. You have seen this, right? X belongs to A, right? X belongs to A. Do you see this is same as this? I know, right? Okay. Do you see this is same thing as this? Yes. When we are saying this is set, okay? I pick one X from here. Okay, what I'm doing? I'm choosing, right? I'm just exactly choosing from all elements of my set, exactly one element, right? Is it clear? So, this function, my domain has how many elements? Only one element. How many elements I can choose here? How many choices I have? If star is fixed, okay? And then we can associate how many elements here? Only one element, right? Because by function we said star cannot go to in two places, right? So this star only can be associated with one element. That means when I'm saying I'm picking X, why don't we just say I'm defining a function where I'm just picking this person? The star goes to X or associate to X. So an element belongs to a set. If we wanted to write it in the same way as we write other laws as a function, is nothing but a nullary function. So each time we say an element is in a set, actually we are defining a nullary operation from a singleton set to that set. So I can even tell this function, name of this function as X, just for sake of simplicity. We just say that choosing X is nothing but a function, a nullary function from a one element set to set A, because I'm exactly associating my star with only one element. Okay. Can you give me an example of binary operations? And this one, even you know since you born, almost, high school. Multiplication, addition. Do you see? All these are binary operations, long before you heard the word even operation. Okay, so these are nothing new. You actually learned in school. 2 plus 3 is equal to 5. This is nothing but a function. 2 plus 3 is just a function. So if we wanted to write in a function notation, so this is our f, serial number. Then we take t, and then we take t. Then we say 2, 3, and we associate it. But if we write by function notation, then it should be written like this. But we don't write like that way, but we put this plus in between. So that's just a matter of notation or convention. Instead of writing like this way, we write like this way. But essentially, it's just a binary operation. Similarly, multiplication is a binary operation. Okay? Good. So, if we have a set with, so first we had sets, no operations. Number 2, we have a set A with a binary operation, say called it M. Nothing else, a set with a binary operation. It's already a mathematical structure. By any chance, do you know the name of this? I'm not expecting an answer, but maybe you have seen in Pick and Pay or Checkers somewhere. This one. Just a set with only a binary operation, no other property. This structure has a name, which don't appear in algebra books, unfortunately, or at least the algebra books we generally, unfortunately, follow or prescribe. It's called magma, not the volcano, just the name magma. Okay, so now we are building structure. What can we do? We have a set binary operation, okay? Now we put some condition on our binary operation. So make the binary operation is associative. What does it mean by associative? Whether we do the first operation or the second is exactly the same. So now we have a magma. And name is associative. So if we write by that notation, then say let's use the plus notation. What does it mean by associative? This is an example of associative. Are there any questions? Not really. That means whether we do the first operation with the first 2 people and then the second one is the same as the second 2 people and then the first. Okay. So this is just a typical example of addition become a binary operation. So if we have a magma with M associative, what is it called? It's slightly better than magma, right? Because we put a condition on our binary operation, which is associative. What is it called? Any idea? Once again, it does not appear, unfortunately, in the books. Because we don't teach algebra. We just give certificates, right? We don't teach these things. But believe me, once I tell you the name, the structure, and if you Google, you will see how much research is happening on this without topology and with topology. It's called semi-groups. You never heard, right? Semi-groups. You had groups. So life starts from groups, right? At the university. You see, there is whole thing underneath of these things. And these are equally important. And there are a lot of things. Even if you are working on function analysis, there is a whole research area called semi-groups of linear operators. By the way, there will be a very special workshop just before the SAMS conference at Nelson Mandela University, where Professor Jacek Banaszak is going to give a seminar talk. It's actually a series of talks on semi-group of linear operators. That's one of his research field. And he was also, by the way, my former PhD supervisor. Yeah.
So different issues.
Yes, I didn't reach yet group. So this is semi-group. Now will come some group. Far down. You see, here only your binary operation is associative. Now, no other condition. Group has much more condition. So this is called semi-group. So now next, if we have a semi-group, and then we add one unary operation with it. Unary or nullary? The next one. We just add one more nullary operation. We already have one binary operation and then we add one nullary operation. Nullary operation means selecting one. And that structure is called monoid. Now, what is this nullary operation? Nullary operation is saying we pick up somebody. Now you know what is the definition of a group, right? Do you recall that in group, in the definition of a group, one of these condition was there exists an element E called identity such that X star E equal to E star X equal to X for all X belongs to G, right? So you pick up an identity. You say there exists an element, right? E. But what is that? There exists an element means is nothing but a nullary operation. Because we pick up someone. And there's exactly one element we are picking up. For that operation, we are calling nullary operation. So it is a set A with a binary operation, which is associative, and let's call that nullary operation E because we pick up some one problem. Yes.
So what is the difference between null and then the unitary?
Unary operation means like your inverse operation. I will tell you. Like you associate, it's just a function. This is unary. Nullary means one element to this. So you pick up just exactly one element. There exists an element E. So you pick up.
Nullary is the identity.
Identity. Existence of identity can be said or represented as a nullary operation because you pick up exactly one person from yourself, whom you call identity.
So unitary is the inverse.
Unitary is the inverse. Why? Because it's a function from G to G. Do you see? Because for every element you associate somebody. Whereas identity, you have exactly one person, right? And that's one person is represented by this nullary operation. Okay. And of course, it satisfies certain properties with respect to this E. Because if you have every element A, and if we just write star with your usual notation, something like that. And this is called a monoid. Okay. Now you come to groups. So tell me, from monoid to group, what in terms of operation, what I need to add? I already have monoid. I wanted to go to group. What else I have to do? What is missing? So group is a monoid with another unary operation. Why unary operation? Because what group is saying that the additive group, right? We write like this. So it says why I say that inverse operation is a function. I will cite the paper. Who is the inverse of 2? Nations. With addition? Negative 2. Do you see what I'm doing? It's just a function. For every element of my real number, I associate exactly one person, right? So it's just a function of which type? This type. And we said this type of function is called unary operation. Okay? So what is a group? So if we have a monoid and then unary operation, . So let's write it like this. Then what we get is called a group, where of course, this inverse again, we don't write like this way, but we just write, I mean, we don't write as a function like, does not go like, we don't write like this way, but we put on the other side, right? Just a matter of notation. So you associate A to somebody, and that somebody is written like a to the power -1 if it's a multiplicative, or if it is additive, then we just write minus, depending on what notation we use. That's how you have seen in the book. But essentially, this is nothing but a unary operation. So of course, then it should satisfy as usual how it's written in the book. Equal to identity. So do you see how we are building structures? So this is mathematics. So if we see even the definition of a group very structurally, it actually has lots of things. And before you reach group, I didn't start from group. I start from nothing, from just set. Then we just put more, and then we go like this way. Okay. I'm sure like University of Johannesburg at SMU, which module you studied first? Linear algebra or abstract algebra? As you know. Linear algebra, right? This is nonsense. Don't worry, I will do the same. This is nonsense. You cannot tell the definition of a vector space is most generality without knowing the definition of a group, without knowing the definition of a ring, without knowing the definition of a field. But we study field, we study vector space, then in third year you have abstract algebra, right? Where you study groups, maybe rings also, right? Or no? No rings. Depends. Yeah, depends on weather, temperature, everything, right? So you study vector space, then you study groups, then you study rings, then you study fields. Whereas the whole thing should be upside down like this. Now you may ask, why you are doing this crime? We are doing this crime because, to best of my knowledge, in whole South Africa, there is no curriculum in any universities which is only for mathematics students. It's major mathematics, physics, major mathematics, computer science, major mathematics, something else. Okay. And first year, even disaster, right? Everybody is there in something called calculus, which even does not make sense. 300 years ago, it makes sense, but not. You do calculations and calculations, you find integration, differentiation. Why we are doing this, we don't know. We are just doing this because we passed the module. Linear algebra, what do you do? Matrix, multiplication, addition, eigenvalue, inverses. Why are you doing this? We don't know. We just pass the modules. And if you are an engineering student, that's the end of the life. Oh, I will not see mathematics the rest of my life. So you are so happy. But if you are doing mathematics, oh, this just started, go to the third year. But because of this upside down whole curriculum system, it confuses you upside down. Because you never see the connection of your linear algebra module with the abstract algebra module, and then Maggie Aphane is teaching functional analysis. What is happening? Professor Aphane is doing functional analysis, and what is functional analysis? Functional analysis is the marriage of two different mathematical structures: vector space, topological space. That's it. You don't believe me? Okay, maybe I will not have time here to reach up to functional analysis or something. But if we learn mathematics systematically and step by step, building blocks like this way, then it's not complicated. Then we see how the connections of things are happening. And when we say, I'm working on functional analysis, I'm an algebraist, I'm a topologist, I'm a category theorist, this is a disaster. And why these people don't talk with each other? Because our education was not done properly. It was not showing us the connections of these areas through these mathematical structures. And that's the problem. And that's why you are getting confused. And we say, oh, I'm an analyst. What do you mean by I'm an analyst? You are doing algebra. You are also doing topology. But we are not aware of it. Yeah, yes, ma'am.
Okay, thank you, Prof. I just want to make the remark that we had in the morning when we were talking about this. During breakfast, we did have some sort of this engagement, how we gonna bring all of the class together. And then my remark was, it is good for those who have already built their research profile, knows their mastered their fields or their area of specialization. At least if I've mastered topology, then I'll be able to learn and connect with whatever module. Then Prof responded and said, no, actually should be the converse way. Those who are still studying, this is the time when you have to see the networking. Don't be selfish or stereotype like us. This is the right time for you to see the connection and you study everything at the same time. So I wanted to pass that. Thank you.
Thank you, Maggie. This is very important, and this is another fact. In South Africa, to best of my knowledge, very few universities offer coursework-based master's program, right? Tara will be so angry because he was shouting the same issue a couple of weeks ago at our LMS meeting, what Zurab was telling. It is another crime.
You see, what happened was they toned down, they reduced the coursework in the honors degree to the point where it's now so restricted so that you don't have a very broad sort of knowledge on mathematics at the honors level. So when you come to the masters, they avoid the extra coursework, so you just do the research in a very narrow area, and you have no knowledge on broader mathematics. So that time, what I was saying at that meeting was, our honors in the old days had 10 topics, but you were encouraged to do another 4 or 5. So you would end up doing about 15 honors topics in, say, pure mathematics. Maybe 3, 4 will be in applied maths. Maybe the applied maths guys will do 3, 4, 5 from pure mathematics. Maybe even 1 from physics, something like that. So you have a very broad thing. You do lots of function analysis, lots of group theory. I did lots of function analysis, topology groups, a lot of it, and 1 or 2 applied maths topics when I did the pure mathematics honors. So when you came to the masters, you were pretty knowledgeable about mathematics. And in addition to that, generally the masters you would do will be coursework in the first half and a dissertation in the second half of the masters. Now, your honors has been reduced in terms of broadness. And when you get to the masters, you're doing no coursework. Unless the supervisor will tell you, go and read some material on this particular topic because you are going to need this for your dissertation or it's extra knowledge, but it's still very narrow. Unfortunately, is the structure of the honors and master's programs in South Africa right now. That honors program, my argument or my criticism was, comes not from the universities, comes from the Department of Education. So you can't change the structure. I would like to change it back to what it was for obvious reasons, but you can't. Yeah.
Okay, so once you have groups, then we can add 1 more binary operation. So groups. By the way, if this binary operation is commutative, what that group is called? Abelian group or commutative? Okay, so these two are same. So if we have an abelian group, and then we have another binary operation such that we distribute. So let's write it by multiplication. E dot, and let's write this operation. And since we didn't say this operation is commutative, of course, we have to consider the both sides. Now let's try to understand. We said that we have an abelian group, another binary operation. Now you may ask, why we need these two conditions? It's already a structure and I put another extra structure on it, right? But why I need these two conditions? Can you see? If I just say, this is my structure, what will be the problem? I have an abelian group with extra multiplication. So I multiply two elements and I get an element. What will be the problem if I drop this? Problem is, this is already a structure, right? This is another operation. How this one interact with this? This has binary operation, right? I'm saying I'm introducing another binary operation. But they should talk with each other. Otherwise, there are no connections between them. And that is why we have this distributive law. So distributive law is actually connecting this structure, which is already there, abelian group, with this extra binary operation, multiplication, and multiplication talk with my addition. So if multiplication is commutative, of course, I do not need two. Only one is sufficient. But if multiplication is not commutative, then I need multiply on both sides, right? Because either this side or that side. What this structure is called? Any idea? It's a commutative group already, but a commutative group with another multiplication binary operation satisfying this problem. Yep. Rings.
There is a question, Prof.
Yeah.
What is the difference between linear algebra and what is a simple function?
I'm not quite aware of the fuzzy kind of mathematics, but Abdul, do you know fuzzy?
Fuzzy stuff. No. I mean, I've heard that concept quite often, but I'm not quite sure what they.
Yeah.
Attended one or two talks about fuzzy algebras and so on. I'm not quite sure what they actually do.
No, I also heard about it, but I never.
I've attended one or two talks, but I never quite got the hang of it. One needs to study. I don't think there's any South Africans.
No, there are people in Rhodes University who works on fuzzy algebra. And, yes, I heard from Zurab. But Zurab can actually answer a little bit better on the fuzzy algebra because he has some interactions.
Some interactions.
Sorry, I couldn't answer that question. So this is called a ring. And then ring can have another unary operation which is called multiplicative identity. Yes.
So isn't ring need to satisfy is it similar to group?
It's already packed in this box. All the conditions are packed, and that's the way how we should do mathematics. When you come up with the definition of a vector space, you remember, they state it's a set V, and then real number, and then 1 million axioms, right? And you forget, did I miss some axioms?
I think what he's asking is,
I know this.
what's the difference between a ring and a group?
No, I know this condition in the ring, but is a binary operation to be a ring need to satisfy the.
No, it's not a binary operation. We have a group structure already, abelian group. Then you put another multiplication structure such that it satisfies this. But this don't written like this way maybe. They unpack this whole thing each time and they write all the axioms of abelian group itself. And we don't write that. Because we already built these structures. Why should we write it again? If we need, then we can disclose it. Did you feel the problem?
I think the fundamental thing is that a ring is just a group with two binary operations. I think you just
exactly. It's already an commutative group with another binary operation which interact with your original group operation like this one. And that's it. It's like if you go to the shopping mall, do you prefer to carry everything like this or do you want a trolley?
The trolley.
Of course. Do you want it to put in the bags or you wanted to keep everything on the trolley just like that? You want bags, right? We are putting them in bags such that we know in which bag what is there. If I have to remove and swap, okay, I have this bag, this, and I have become this. It's impossible all the time carrying all these loose things. That's the way how your definition of vector space appears in the book. It says, I've said V and a real number, and then list of 10, 12 axioms. But we can put them together in boxes like this way, and we know where is what. Then there is no chance, did I miss one axioms? That question will never come because you just ungroup each of these boxes. And once you ungroup all the boxes, you get whole list of things. You will never miss it. Because every axioms is in some boxes. And that's the way how we are trying to do. Because this is the way, structural way to understand matter. Then you see who is where, how the things are coming. It's not that some random axioms are here and there and they are interacting with each other. It's actually interaction between mathematical structures. That's what is happening. So let's go to the definition of, still have a bit of time, and then vector space, and then it will be clear. So if we have a ring with another unary nullity operation, and then that's called ring with identity. So now we just write this as an abelian group. So everything is already there. We have multiplication and we have multiplicative identity. Example of ring with identity. Example of ring with identity. Identity means multiplicative identity. Real number. Take your set as real number. Take your original group structure as class. Okay, addition. Do you agree that addition is commutative? 2 plus 3 is same as 3 plus 2. So it's an abelian group. Do you agree? Then there is another binary operation called multiplication, right? I can multiply any two real number and it will be a real number. So it's a binary operation, guaranteed, right? And do you agree? Those things satisfy this property. In fact, you don't need to because multiplication is also commutative. And who is multiplicative identity? The number one, right? Because what does it mean by multiplicative identity? If I multiply any number, real number with that number, I should get back that number, right? So 1 times 55 is 55. Okay? So real, in fact, if I just put R here, then it's actually a commutative ring with multiplicative identity. So from here, we need little bit. If every non-zero means additive identity. If every non-zero element has a multiplicative impulse, what is it called? Wonderful. My students never heard division rings. You are way above of them. Fantastic. Maggie, these are incredible. They know what is a field, but they never heard of division ring. Thanks to function analysis, because it's not commutative, right? So it's called division ring. So when your multiplication is not commutative and this thing is happening, then it's called division ring. And when your multiplication is also commutative and this thing is happening, what is it called? Field. Okay, so it's a non-commutative version of field is division ring. Very good. So without non-commutativity is a division ring, and with commutativity is called field. Now we are almost ready to tell what is a vector space. One more thing. There is something called M action, where M is a monoid. What is an M action? So if you take a monoid, you take any set and you define a function. M is a monoid, A is any set. M is a monoid. Okay, A is any set. And you define a function. like this one. And believe me, you have seen this. You remember scalar multiplication in vector space? Scalar multiplication. So how was that? It was like this, right? Isn't it? Real number, any vector, and this. So you generally write alpha, you write v, and then you write alpha v, right? That's the notation what you use. So you write generally alpha v, and then you associate a new vector which is called alpha, and that's called scalar multiplication. And this structure, a monoid, and you don't need real number. To define a MAME action, you only need monoid. So it needs to satisfy only two properties. One is that if I take one, and if I take, say, A, one is the identity of your, I shouldn't use V because it could be confusing. So this is an example. 1A is equal to A. Okay, so that's the one condition. You have seen this, right, before. You remember 1 times V equal to V. That was one of the axioms. And there was another condition. What was that other condition with respect to scalar multiplication? If you have alpha, beta, and if you multiply them and then you add V is the same as you take beta V and alpha, right? So that condition was like this. So let's write like this one. M1, M2 times A is the same as M1, M2, A. That's it. What is the named action? Take a monoid, take any set, define the function. This is not a binary operation because your sets are different, M and A. And if it satisfies these two properties, that's called a named action. Now we are ready to define a vector space. Can you believe this? So much mathematics is missing before you do linear algebra. And do you see how far we went up to field to tell what is a vector space? And I still didn't write the definition of a vector space. And you need the definition of a vector space if you wanted to do it structurally, all these things. I mean, you don't need monoids, but monoid comes from groups because to define group, you need a monoid. So finally, what is a vector space? For vector space, you take a field, you take an abelian group, and you take an M action, F action. That's it. Your all 10 axioms are sitting here. I don't write anything, I just write like this. Do you remember you had alpha, beta, there were many lists, right? Alpha plus beta plus gamma equal to alpha plus beta plus gamma, right? But that's already filled one of the axioms because that actually comes here already in associative with long before there. All the properties of your alpha beta multiplication is filled, right? So then you said alpha times 1 is alpha. Yeah, of course, because it's a field, it's a ring, commutative ring with a multiplier version. Everything is there. So all your 1 million axioms now packaged in 3 mathematical structures. All of them are there. And you don't need to recall where there are 10 axioms, 15 axioms. No. I just need to know I need a field, I need an abelian group, I need an action of the field on my abelian group. And that's it. And if somebody asks, what are the axioms for field? Okay, I know field is a ring, special type of ring. Then you disclose. If they wanted to go further, what is the group? Then you go further. But why should I always open whole box when I need to just find one thing and keep it in the box? So we reach at the vector space. Now, very quickly, your topological space is not of this type as a mathematical structure. It's a little bit different. Where we take a set and we take a set of subsets, right? Maybe you tell me, what is the definition of a topological space? So we generally X will be also there. Next. Finite intersection. Huh?
Finite union.
Both finite? Can I not push this? Which one? So depend how you define your topology.
Union is finite. Sure.
When you said you are not sure, have you ever realized what causes that uncertainty? Exactly the same reason, if I have asked you what is the definition of vector space, you will not sure what are 9 axioms or 7 axioms. Because we memorize. We think there is something and there is something, but we don't see the connections. Once you understand how we build topology, then you will always be sure if I wanted to define my topology by open set, then which one will be finite? And if I wanted to define my topology by closed set, which one will be finite? But if we wanted to memorize it, there are some action. Because we do not see how we build things up, where from topology came, what are these animals, open sets, closed sets, how they came up. If we start from real numbers, say calculus, actually when you are doing calculus, you are doing function analysis. Not only you are doing topology, you are doing function analysis. You don't believe me, right?
They don't see the connection. Why is it required that connection?
Have you heard the word called norm?
No.
No. You very much know, right? Because you work with every day. Did you see that double bodyguard? I call it double bodyguard because it gives you a protection from negativity, right? Do you see that double bodyguard was already there in calculus? You just remove one bodyguard, right? What is absolute value? Do you see this absolute value is your master's or honors project? No. It comes in a more general setup. Then you have this formula, right? Mod of norm, now norm, right? Double bodyguard, double protection, right? Double protection, x plus y less than equal to norm x plus norm y, like this thing. But you already know this is in the real number, right? Absolute value of x plus y less than equal to absolute value. And now, Professor Aphane told you, metric space, right? D of x, y less than equal to. This is just a generalization, the same inequality. It's the same inequality. Your first year calculus is actually function analysis over real numbers. When you do complex analysis, you are again doing certain level of function analysis in the complex numbers. Because you are studying this vector space structure with this norm. Why you need norm? Because you wanted to talk about convergence. And when you do not have a luxury of a norm, then you go for the metric space. When you do not. What is our goal? To understand distance. The goal of norm, goal of absolute value, goal of metric space, goal of topological space is to understand the nearness. How the 2 points are close to each other. So this proximity, to understand this, even there is a space called proximity spaces, which is more general than topological spaces. But the whole idea of this calculus, this analysis, this topology is actually a combination of algebra and this understanding the nearness.
That's why I have a question for you.
Yes.
Question is the following. I don't like hunting. I'm against hunting. But this hunter starts at his house. Follow my directions, right? Starts at his house and he goes 1 kilometer east. So this is, east is there, right? He goes 1 kilometer east. Then he goes 1 kilometer north. Follow me. He shoots the bear. Goes 1 kilometer south.
Along the same path.
South. Where do you start? Home. 1 kilometer east, 1 kilometer north. He shoots the bear, comes 1 kilometer south again. And he's at home. What's the color of the bear? What is the color of the bear? That story, that is the picture I want you to see, but you need to now think. Professor Goswami spoke about distances, how you measure distances. Take a ruler and you measure, right? Yeah, not always. That's the picture. 1 kilometer east, 1 kilometer north, he shoots the bear. I'd like to shoot him, but anyway. Then he goes back 1 kilometer south. So you are north and then south again 1 kilometer. But he's back where he started, at his house. What's the color of the bear?
The color.
The color. Blue, brown, black and white in the case of a panda bear.
That's a question where you will think while giving the answer. So topological space, or very quickly, how things will happen.
Sorry, they're not going to think about topological spaces now. They're thinking,
Where is the
oh, bear.
Okay. We don't have time for going further, but just very roughly speaking, how this analysis comes. What analysis we are doing. How algebra and topology talk with each other. Imagine I have a group. Just additive group. G for G. Addition. So it's an algebra, right? Algebraic structure. Now I wanted to put topology. How to do that? What is the minimum thing I need to put here so that I can do topology on these groups? No distance. I just make my operations continuous. Continuous as a topological functions. Right? You know the continuous functions. So whenever you have these algebraic structures and you make your operation continuous, you get the corresponding version of it. So you do topological spaces, you do groups. And when you make every operations of these operations, what we said, continuous, then that becomes a topological group. So when you do function analysis, you have two operations. One was the scalar multiplication, another was vector addition. Right? In a vector space, you have scalar multiplication and vector addition. Now you wanted to do function analysis with vector space. That means I need to put topology. How to put topology? Make these two functions continuous.
That's why we come to
Yes, when it is an algebra, no, this is not even a homomorphism, but when addition is a homomorphism, yes. But when you make that homomorphism also continuous functions, then that becomes a topological vector space. And when you work with a non-linear space, that's a very special case of topological vector space. So you can do the same thing with any one of these algebraic structures I talk about. You can take a semigroup, make your operation continuous. Then you are working with a topological semigroup. You have a ring, you make your ring operations continuous. You are working with topological rings. And when you put topology on your vector space, that's your function analysis. You don't believe, right? No, I completely understand. The point is, as Professor Janelidze mentioned, our focus is to understand these structures and connections between them. And if we see like this way, then I'm an analyst or I'm an algebraist, these kind of separations will not come. And then you feel the connections between these two. I mean, what Professor Abdul is working is something called Lie groups. You never heard of. You don't need to heard of. Simple. There is something called manifold, which is a little bit complicated definition. Okay? When you do group structure on manifold, that's nothing but Lie group. Simple. When we define group, we start with a set, right? Then you put a structure. So your underlying set was set, and then you put a group structure. Then it becomes a group. So instead of set, imagine I have topological space. Then I put the same operations like this way. That will become a topological group. And instead of topological space, if we have a manifold, smooth manifold, and I put the same group structure, then it becomes Lie group. And if we see like this way structurally, then these different areas I mean, of course, I'm not saying that just telling you the definition means you learned everything about Lie groups. Of course not. That itself is an infinite area. Any one of these is an infinite area. But at least you will not feel that I am an alien when I'm talking with Professor Kara. No. You are working on groups, you know topological spaces, and you extend a little bit, you know as a manifold. Oh, okay, you are working group structure on the manifold. When you are working on function analysis, it's not that I am not working on algebra. You can't do function analysis without algebra because it starts with a vector space. Whether you are a Banach space or Banach algebra or sister algebra, just look the definition. It is here. Most likely you work with complex because complex works very nicely in function analysis, not real. Generally complex because the spectrum become non-empty. That's why you work. But if you are working on, say, financial mathematics, what are you working on? A probability space. And what is a probability space? It's a sigma algebra, and you define some function. So it's again a mathematical structure. So whether you work in algebra, analysis, topology, dynamical system, what is a dynamical system? Dynamical system is nothing but an action. None of these standard books of dynamical system even bother to tell the definition of a dynamical system. They said, it's some kind of thing, right? It's not some kind of thing, it's absolutely very precise thing. If you want a positive time, then you take this as a positive real number with 0, which is a monoid. And then you take an action on where? Topological space. If you wanted to do ergodic theory, then it's a measurable space. So you just take an action of this monoid on them. So you are just doing this structure. Of course, then it itself is a big field. But then you see the definition of the same action, which appears in your definition of vector space, as well as appears in the definition of itself, what is a dynamical system, is the same thing. Of course, if you wanted to study, you need to study in details, but at least it tells you, no, it is not absolutely unknown to me. I know what is a vector space. It's already stellar multiplication is there. And this is the advantage to study mathematics structure. Then you choose whatever the structure you will do, master's, PhD, that's your goal. But if you see this connection, then if you have lost somewhere from where I should look for the tools to solve my problem, maybe my own tools in my structure is not sufficient, then I borrow tools from another subject. For example, this whole subject area called algebraic topology came out to solve topological problem which was inadequate with the tools, and then you take the algebra help with the groups. And knowing these connections is actually tells you, okay, so this is, so, and when you go a little bit much higher of these different mathematical structures and think it's categorically, then it's like a sitting in a satellite. And because if you are on the ground, and if you wanted to say, well, where can I get gold, here or there? Of course, you cannot dig on the whole earth, right? So you go to the satellite, get a radar one, get in X-ray or something, underground here is this. So when you look from the categorical perspective, then you get a much bigger picture and you see, okay, this is connection with this, which you may not be able to see when you are sitting inside a group. Because when you study groups, you study something. When you study vector space, you study something. Maybe you are studying the similar things. And when you study in a very high level, then even you see the connection between these different mathematical structures. So here I just give you very, very basic definitions of some of the very, very elementary structures and try to show you how to build from nothing slowly one by one. But it can carries on. I mean, all these algebraic structures actually set or mini sets and a bunch of operations, and they satisfy certain axioms and then interact with each other. And then you know the topology. If you wanted to topology and algebra, you get topological algebra, Banach algebra, D groups. All these are examples of interactions between algebra and topology, but different combinations. I can do the different combinations. I think we are over time, right? Go for now, photo.
What's the color of the bear?
Yeah.
That was a very nice presentation, but before we go on, I just want to get input from the students.
Yeah, sure.
With the presentation, putting together, how was it? Can you talk to us? How was Prof's presentation? Okay, yeah, noted.
For me, the way it's structured from sets, links to now participants. I didn't think about it in that sense because I was taught this, and then the next year I was taught this. The next year I went back and I was taught groups that are. So I now have a bit of structures to what I'm making and then what I'm going to connect. Yeah, that's what I think.
Was it helpful?
Yeah, very helpful.
Is that how you will wish to be taught?
Well, please.
Okay.
Yes, okay, so thank you very much for the call. From my side, yes, he covered me partially, right? So from my side, it's more on what we learn about relationships mathematically, right? I feel like it's like you said, it's an important part that we have missed within our academic journey. And so we study bits and pieces here and there. Then when we get to the highest level now, start to become confused. What is this? What is this? Where is this thing applicable? So I feel like obviously this should be the standard of mathematics. From especially lower levels, when you go up, it becomes far much easier for us to be interactive mathematically, right? Because personally, sorry, I felt like there was maybe like a crack or a maybe
Barrier.
maybe yeah maybe like,
Something
a
is-
barrier, right? Between mathematics and its applications, right? Okay, mathematicians, they do this, then how do applied mathematicians feature into all of this? So if we speak about structural mathematics, that's when we can now break that barrier and say, okay, no, in fact, we're all doing this, but this is what we're applying to the mathematics that we have. Thank you very much.
Sure.
Thank you.
Another input? You want to say something?
But connections. The means.
Any kind of applications. I mean, as I said, my PhD was in mathematical biology. You can always make a model. But what's the point if that model is not related?
Useful for the.
Sorry, we can't hear it, yes. So what's the point making a model for the financial mathematics, which cannot be used in the stock market or share market? No, I made a model, I wrote a paper. So what? It's useless. It's as useless as my semigroups. Right? I wrote on the board, so who cares about these semigroups? But if you really wanted to do a model in the real world, believe me, it's extremely difficult. It's not a so toy model. I'm sitting in my room. Let's solve Ebola problem today. You can't solve Ebola problem today without knowing the whole biology, because when you get that how actual model construct, maybe if you are working on applied mathematics or you heard, they may not tell you. First, you collect the raw data. Say if it's a biological science, say some epidemiology, say some plague or something. You go to the hospitals and you collect the data, either you or some standard source, they get the raw data. Then you have to refine that data using heavy machinery of pure statistics. Because that raw data is absolutely useless for a mathematician to construct a model. So from that raw data, you actually filter it out. Then you construct some kind of distributions, continuous, discrete, depending on that. And it could, in the most of the cases, it will be probabilistic, because the real world is not as nice, as beautiful as I'm writing here, as Zurab mentioned that. Because it's very, very undeterministic way. It's very stochastic, it's very probabilistic. So you construct these probability structures of this thing. Then from there, you construct a mathematical model. So you got the model. It's not the end of the story. Then you do your gymnastics, whatever the area of mathematics you know, to get some conclusion. You prove some theorems on that model. It's still not end. Now you get some conclusions mathematically, which is practically maybe completely useless. So you go back to the realizations or interpretations of these mathematical calculations or analysis, whatever you did, to the real world to check
where from I started, does it work? Does it match? Does it give some predictions actually? If not, forget it. This whole process is complete nonsense. Of course, it can happen few times. You go, you correct. Few time you go correct. And that's called actual applied mathematics. It can be any area. It could be in engineering, it could be financial mathematics, it could be mathematical biology. Depending on the size, this should be a whole continuous process, and that should be involved very relevant people, like these different mathematical, not mathematical, these focus areas where you find these people are there. So if you really wanted to do an applications in biology from the mathematical perspective, of course, you have to talk with Professor Hugh Kang. To understand that thing, you have to talk with a doctor. I cannot solve a cancer problem without knowing anything about this. I mean, this is fake. How can you solve it? You have to be collaborating with such a person. Otherwise, it's just a... So applied mathematics is not bad. Applied mathematics is equally important. I mean, all our computer is applications of Boolean algebra, absolutely Boolean algebra, which is a pure mathematics, and this is absolutely applied. This is called applied mathematics. So if you like applied mathematics, go for applied mathematics, but don't have this idea, I can do applied mathematics without knowing any mathematics. I mean, how is it possible?
And the other way around.
And the other way around.
And the other way around, as you see, Professor Goswami is very, very knowledgeable, both in pure side and applied side.
I'm working in a applied mathematics area, but I love to teach the abstract algebra, group, ring, fields. I love to teach those structure, but I'm working in an applied area, working on differential equations and more particularly in the applied side. But when I teach, I love to teach groups. So I enjoy those structures. So if you are working in applied, doesn't mean you don't have to touch the.
But differential equations also give us mathematical structure, dynamical systems.
Exactly. But what I'm saying is, for example, if you are working in applied, so don't ignore the beauty of these structure as well. Because when I study and teach and discuss, I love to discuss these structures.
I think there is also a bit of historical habits. I mean, do you prove theorems in your papers?
Yes.
Can you give us an example of a practical application that's been implemented in the industry that comes out from your work?
For example, the mathematical models and the treatments. For example, there are some models in biological sciences. For example, the very important example is the machine you use to calculate the.
Is it your work that was implemented in industry?
It's not my work, but I'm talking
so you're
about
a pure mathematician.
Right.
So you're a pure mathematician. If in your papers you prove theorems,
yes,
and you haven't yet produced something that's implemented in industry, it means you're a pure mathematician.
Right. Yeah. But I'm saying.
What I'm saying is that this terminology, pure applied, is a historical thing. Yes. So there was something that was called applied, and then it kind of stayed over.
So it became fuzzy.
I tried to answer, but I don't think I did a very good job. Do we have a comprehensive treatise on the interaction between these concepts? Otherwise, Professor Goswami should consider writing a book for publication in this field. Professor Goswami, it's a homework for you from our focus area. We're all going to help you. Please write a book for us. Next item in the program is a photo. But before that, Professor Aphane.
I think we did not do justice with Prof. Goswami. I didn't know that the session was going to be so interesting. 1 hour was not enough. That's what I can say. Thank you very much.
What's the color of the bear? Anyone?
That question, by the way, is a very applied question. If you think of it only mathematically, in abstract way, you're not going to be able to answer it. Think of it in a very realistic, applied way, and then you'll be able to answer the question.
The reason that question came up is when you said there's this whole thing about how you measure. Like, yeah, we know how to measure. Flat, it does measure. Right? When you're walking up Stellenbosch Mountain and someone asks you, how far have you walked? Suddenly the question is not so easy anymore. Because I can tell you I walked from here to there, 1 kilometer. When you're going up and this, so on, it's like, how far have you walked? It's how you measure things, depending on the shape of what you're doing, or where you're on. This is easy. It's flat. It's easy to measure. So how you measure depends on what the geometry of the thing you are on, the object.
So what colors the vision?
No, that's the hint. That's the hint.
The hint.
It's giving you to find the answer. So measuring very much depends where you are measured. Because it's not a straight line, right? When you are working on a path or even on the surface of the earth, right?
So when Professor Goswami drew that picture correctly, it didn't seem right. Because if you go like this, you come back there, not where you started. Because he drew it where? On a flat board. Flat, emphasis on flat board. But I'm saying you with certainty, the guy actually came home.
I think
How did it happen?
we shouldn't give more hints, Professor
I
Kara.
think that, yeah, then I basically answered the question.
You have an answer?
No, first he went across. He went straight across, 90 degrees, straight up. And he came straight down, same distance. But he didn't land here. He landed at his house. Or his home, his igloo. Give the answer.
So, next item in the program, we will come back to that question and hopefully answer it. Next item on the program is a group photo. We're going to take a photo in such a way that we can also see maybe Nithex behind in the photo. Please don't leave yet. You can leave your things here though if you're coming back, because this room is locked as you see. So it's a group photo. After that, we'll have lunch at Nielsen Student Center. Everybody gets their own lunch. And then there will be a so what we have currently on the program is Stellenbosch University campus tour for 1 hour from 2 to 3:15. The question is whether we want to keep it that way or whether there are some ideas to do something else instead. Are you happy with that? But if we do that, I need a local, because I'm not going to be available in that time. So either Kishan or Elena will have her mini school during that time. But it will probably not make sense for us to join your mini school because I already told them about your mini school, so it probably doesn't make sense to do that. Who will be available locally to give a campus tour? Because I will not be from 2 to 3:15. Do we have any volunteers?
I'll be available, but I don't know the campus.
So you see, that's the wrong answer. You shall be available. And when you are lost, you don't tell anybody you're lost. You just make it look like you know everything. Very good word.
Good afternoon, online.
When you're hiking with guys,
Good
you
afternoon.
are lost. Don't ever tell them you're lost.
Good afternoon, online.
Good afternoon. Good afternoon.
Sorry to interrupt. I just wanted to say something from my part or online. How do I collaborate with you? I'm running a 2-9 profit organization, the one who deals with maths and science and robotics. And I'm also giving encouragement to different communities around Gauteng, encouraging
That's fantastic.
mathematics from a young age, because I find that there's a disconnect. People, they just cram and pass, but it's not like a meaningful tool to solve real life problems. So
Let's set up a Zoom meeting.
yes,
Maybe we can meet with yourself, Professor Aphane, myself, maybe Professor Goswami if he's interested. because we have a lot of ideas we want to do in that direction, and we definitely would be keen to see what you can offer from your side.
Yes, yes.
Building names?
Do you have my email address?
I don't have your email address. Let me just put my email address there so that
I'm writing mine in the chat.
in the chat. Okay, that'd be great.
Need to go somewhere after.
Please reach out to us, and I'll set up a meeting. We can meet over Zoom and to discuss these things.
Just don't go.
Thank you so much, eh?
Thank you very much. Thank you very much.
Yes, now we're going to leave. We're going to get food now. We're going to be back at 3:30 for presentations by SMU honor students. I don't think there will be any online activity before 3:30.
Oh, okay, so 3:30. And also the one who is professor who's from SMU.
Yes.
Yeah, from SMU recently at Innovation Hub. I was involved with the students from SMU dealing with the hackathon with their students there.
Yeah, that's something that NITEX would be actually quite interested in. I'll also put you in touch with the director of NITEX.
Okay. Oh, thank you very much.
Thank you so much. Thank you for reaching out. Thank you.
Thank you. Thank you. Bye.
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 Welcome back to our online participants. We will start in a moment.
You can help us. Sorry. Can you increase the temperature of this room?
Yeah, increase the temperature.
Yeah, we can pause there.
Sorry.
Is it cold now? Right. We can go.
Yeah.
So one first, then must start and then we go to the next.
Inflation being at the table. But at the nice coffee. So.
No, you just look at here also because in the folder side you have a new. And then you remove it. Yeah, close this.
Sorry, can you? Sorry.
Yeah, there's a button there. Is there a button? One. Yes. Your name? Sign. Like this. Here this would be. So maybe we can ask your supervisor, Dr. Renati, but she's not here. Maybe co-supervisor, Professor Aphane. To introduce the series.
Okay. Good afternoon, everyone. Today we are going to listen to one of the master's students about the work that he has mentioned. So the work is not yet completed, so he's still busy. So the topic will be on investigating the existence and uniqueness of this point for us in particular in parliament spaces. So And some, what you have to explain to people from Italian spaces, already you have, here in the morning, how to feel safe with everything. But anyway, share with them what you're doing. Or what you.
Good afternoon.
That's an.
Good afternoon. My name is Khensani Mongwe, and like she said, my supervisor is Dr. Ognadi, and my co-supervisor is Professor Aphane. So my topic is investigating the existence and uniqueness of fixed point of asymptotically regular mappings in Harmat spaces. So this is my table of content, and onto my introduction. Fixed point theory plays a vital role in nonlinear analysis and has a wide range of application in mathematics as well as applied sciences. So the foundation of the field was laid by Banach in 1922 with his Banach contraction principle that states that it guarantees the existence and uniqueness of fixed point or contraction mappings in complete metric spaces. So since then, the results of fixed point theory have been extended to beyond the Banach spaces with the introduction of non-expansive mappings in Hilbert spaces as well as Banach spaces, meaning that they preserve distance but may not contract them. So Perrinde advanced the theory with the introduction of enriched mappings, enriched contraction mappings, as well as enriched non-expansive mappings, as you can see there. So these spaces have generalized the Hilbert spaces, which was conceptualized in mid-90s, and it has substantial work that was attributed to Gromov in 1987, and others that studied the space of curvature bounded above. So this study contributes to that tradition by focusing on enriched mappings, which satisfy a wider range of contraction type conditions rather than classical contractions. So researchers like Kick, Rich, and Gobel have significantly advanced the theory of fixed point in various nonlinear settings, I mean, which is extended to convex and metric spaces. So this study builds on those insights by adapting and expanding them in the geometric structure of Hadamard spaces. So now the results won't just be theoretical; they're aimed at application in areas such as differential equation, optimization problems, as well as algorithms in computer science. So on to my problem statement. Despite the rich geometric structure of Hadamard spaces and their foundation in their foundational role in metric geometry, the interplay between non-positive curvature and the fixed point theory remains underexplored, especially in the context of enriched mappings and nonlinear differential equations. So while Hadamard spaces are well characterized as Kato spaces, the implication of their curvature constraints on iterative convergence and asymptotic regularity demand deeper investigation. Moreover, the application of fixed point results to nonlinear differential equation within this geometric structure of Hadamard spaces is not yet fully developed. limiting the broader utility of Hadamard geometry in mathematical modeling and analysis as well. So the motivation goes as Hadamard spaces offer a compelling setting for nonlinear analysis due to their non-positive curvature and unique geometric properties. However, the lack of unified results linking the structures to iterative convergence and differential equations presents a gap in current research. This study is motivated by the need to bridge this gap, leveraging enriched mappings as well as asymptotic regularity to deepen our understanding in fixed point behavior and its application. So the potential to extend these insights to nonlinear differential equation further underscores the significance of this investigation, which will be properly stated in our significance of the study. So our research question is we have 3 research questions. Our first one is, how does the intrinsic geometry of Hadamard spaces, especially the Kato characterization, influence fixed point behavior and convergence dynamics? The second one is, what are the convergence properties of enriched mappings exhibiting asymptotic regularity in Hadamard spaces? And how do they interact with iterative algorithms? And in what ways can fixed point results in Hadamard geometry be effectively applied to nonlinear differential equations? And what insights can they offer for geometric analysis? So on to our aims and objectives. So our aim is to develop a comprehensive framework that connects the geometric properties of Hadamard spaces with fixed point theory and convergence analysis and applications to nonlinear differential equations. So our objectives is to analyze the geometric structure of Hadamard spaces and its influence to fixed point behavior. The second one is to investigate the convergence properties for asymptotically regular enriched mappings. And the third one is to apply the results to nonlinear differential equations within these Hadamard spaces. So our significance of the study, we have about 4, which is the first one is the theoretical advancement, the algorithmic development, applied relevance, as well as our interdisciplinary impact. So now on to my literature review. So a geodesic path, is the shortest path between points that preserve distance. And the path image is called geodesic segment. So Kato spaces are geodesic spaces with non-positive curvature, and they behave like a flat inward caving space, meaning it's explaining the non-positive curvature of the space. So we have our CN inequality, which says that satisfies an important midpoint condition that the distance from any point to the midpoint of 2 others obey this CN inequality. So more generally, there is one unique interpolated point that is between any other 2 points that respect this condition. So one would ask, why Kato spaces? Firstly, is that because of their unique property, and also their curvature condition that allows a powerful tool for convexity as well as fixed point results. So now the second one will be, they provide a nice setting for iterative methods and optimization problems as well. And I have put a few of the definitions that I'm going to use to prove some lemmas and theorems as well, which are important, I think. For example, here we have a definition sequence, and we have a definition of a Hadamard space, which is a complete ket zero space. And here we have a asymptotically regular sequence, which is a bit different from asymptotically regular. So I gave an example. As you can see, the difference between asymptotically regular sequence and an asymptotically regular mapping is that as the distance between two maps, they should approach zero. And the distance between any 2 points should also, consecutive points should also approach zero. And that is called the asymptotically regular sequence. So this is a definition of an asymptotically regular sequence. I gave an example as well. I also gave a definition of a K contraction as well as a non-expansive, which is going to be important when we're trying to prove contraction. Here I gave an example of a K contraction as well as an example of a non-expansive mapping. So onto my research methodology, where our study design, which adopts a theoretical and analytical approach within the context of pure mathematics. The research focuses on the investigation of enriched and non-expansive mappings in Hadamard spaces, with the aim of establishing existence and uniqueness of and convergence properties of their fixed points. So the study also involves rigorous analysis and exploration of geometric properties specific to Keto spaces. So onto our data collection. As a non-empirical mathematical study, no observational or experimental data was collected. Instead, the data comprises of mathematical definition theorems, lemmas, proposition obtained from the literature, analytical expressions and inequalities characterizing enriched mappings, contraction and investigation of iterative sequence in Hadamard spaces. So the data analysis was carried out through symbolic reasoning and formal proof strategies, including direct proof, proof by contradiction, and mathematical induction. So additionally, symbolic computation software will be employed to verify algebraic manipulation as well as symbolic expressions, and to validate iterative sequence behavior under enriched mapping conditions, and to support the accuracy and reliability of convergence results. So bias, to reduce computational and algebraic bias, the software Maple was used for symbolic computation and verification. So here we have our validity and reliability, as well as our ethical consideration, which involves no human or animal subjects. The ethical clearance will be obtained from SRC and SMUREC. And this is my time frame, which is about 12 months. And my budget, which is about 7,000 or more. And this is my references. Thank you. Any questions or?
So. At some point you were referring to practical applications. Do you have an idea? What are you expecting in terms of practical applications?
I'm thinking, because after I get something from differential equations. So if my result, we get those results, I hope, or we hope we can apply those results to nonlinear differential equations. Then we can enter like real world applications as well. That's what I think.
You don't have any specific practical application in mind yet?
That's it.
Okay. If I understood it correctly, that you are working with nonlinear differential equations, finite.
Yes.
Okay, so to handle nonlinear differential equation, depending on the initial boundary value or one of them, there are various methods, right? It could be asymptotic, it could be finite difference methods and this thing. I mean, is there any study done where you can make a comparison between asymptotic method and fixed point method? Because when you have this nonlinear differential equations, and then when system is generally ordered, then you do an expansion series of velocities, and then you truncate. That's the way. I mean, it seems to me, unless I misunderstood, there could be some kind of comparison or relationship between this fixed point method, because eventually wanted to understand is asymptotic behavior. Am I right?
Enriched person.
Right. No, asymptotic behavior and asymptotic methods are different things. Asymptotic method is a specific method, depending on whether your equation is regularly perturbed or singularly perturbed. So I do not know, because one of my colleagues works on fixed point theory, and these non-expensive maps I heard quite a lot from him. But I never thought about these because you like that. I do not know whether this question makes sense to understand the relationship between fixed point method to do this asymptotic analysis and asymptotic method to do the asymptotic analysis. Because that would be something what we do. The second question is, why Hadamard space?
Why Hadamard space? Because of the unique geodesy. Because the understanding was interesting. So as I was studying and near my supervisor, there was a gap between those understandings and what's this? The understanding from the geodesic space. There's not much study that's going on in that space, is what I'm trying to say.
You mentioned about Gromo somewhere, right, at the beginning?
Yeah.
Because Gromo have quite a lot of work on this geodesics problem on the metric space. Even he has a book on that.
But not in English, but in Hadamard space.
Prof, can I come in?
Yes, please.
I think from what he just presented, what he's trying to do is he's trying to consider a class of mathematics. Maybe I'm not sure. Maybe that class of mathematics defined in space before. For instance,
like non-expensive maps.
Yeah, like non-expensive, like for all this. So I think it's considering an asymptotically regular class of math. So they are trying to take it from that space to a new space and see how it's going to be. So, and regarding the application, I think it's when they are done, they look at the structure of what they have and see where they can apply it. Maybe an ordinary differential equation. I don't know if they plan, but I think they will be applying it to solve a differential equation. That's why you see the existence and weakness of that class of math. So yeah, I'm sure that thing has been defined in a linear space, for instance, Gibson space. It might be defined in K0 space. Now they are now looking at the complete K0 space. Take it there, and you see the geometry are quite different. They have to consider the quasi-linearization of these things and see if it can be defined, and show full complexity, closeness, and the value of life. I think that's what I can.
Yeah, because this is to me something which makes sense in South Africa because we have quite a lot of people who work on fixed point theory. We have also quite a lot of people who work on asymptotic methods of nonlinear differential equations, like my former PhD supervisor. And I never seen these two group talk with each other.
Okay.
Or
I think fixed point theory is being applied to this ordinary differential equation.
yeah, definitely.
But it depends on the nature of this so before you can try to apply it. But I don't know. Like the Thoriso is the investor of Fatlane, but I think they are doing something nice at least considering a new class of mapping in nonlinear space, which is nice.
Since we're talking about mathematical structure, and I don't know what a mark spaces, I'd like to understand a bit more about.
You understand the metric space?
Yes.
So you understand what's the geodesic metric space?
Geodesic?
Like the shortest path between any 2 points to understand the pattern.
Yeah.
So Harman space is a geodesic metric space with non-positive curvature, meaning that it acts like a flat inward space. Don't know if
Space is
yeah, inward can.
I see.
So it's a metric space with a geodesics defined in a path that's way with a non-negative curvature. So it's like a imagine you are doing this manifold theory on the metric space with this curvature things. And then if I understood it correctly, then Hadamard space is the right kind of metric space with this extra structure where you can do this kind of analysis. All of them are here.
Yeah, I think so.
Yes.
Can I just ask one more question? How, so this is something I don't know, but you know, Morton, and maybe the speaker also. So how is this related to differential equations? How do we get a Hadamard space out of differential equations? Or maybe I'm asking my question wrong. What is the link between, because you said that you want to eventually apply results to nonlinear differential equations, right? And then you say within Hadamard spaces. So could you maybe say a bit more? What is the link between Hadamard spaces and differential equations?
Differential equations or just
whichever, nonlinear differential equations, yeah.
Because the aim here is to explore the existence of the.
No, the aim I understand. I'm just I want mathematical relationship between these two topics. How are metric spaces linked to differential study of differential equations?
The part I was trying to explain in might not make sense, but I was saying, since we're exploring the existence of the universe, this fits on the Hadamard space. The point is here to find, well, we find a better mapping for convergence, right? So I'm not yet sure how we're gonna move from that to nonlinear differential equations, but we're still working on that.
Prof, I think the mistake is trying to, I don't know, maybe your question. The thing is, it's not the space to differential equation. It's the problem itself. The space is not related to differential equation. It's the problem, the fixed point problem itself.
Okay.
See that T when it is monotone. You know, all this existence, and it's like you are considering a pseudo-contractive mapping, for instance, that mapping is monotone in nature. So with that monotonicity, we can use it we can write it in form of a differential equation. So it's not the same.
What can you write in the form of differential equation?
When I'm looking at
The definition of fixed point says if you have a map, mapping, it can be a non-self mapping, a self mapping T map X to X. Now that TU equals to 7. That is, when I'm picking any point from that mapping. Like, let me give a simple example. If T of X is X, if X is 1, my function itself is also 1. I don't know if you understand what I'm saying. A map TX, I'm dividing it as X now. Any point, if X is 1, the function itself is 1. Now, what they try to do is they try to play around that operator now. The mapping itself. So they can make T any operator, a monotone operator, a monotone operator. So when they play with the mapping itself, so they make it in a form whereby it's related to a differential equation and try to manipulate and do something like that. Because I've seen them doing it. They look at the operator T, and when that T is monotone, for instance, which I've seen very well, it forms a differential equation. I don't know, maybe you have seen something like that.
No, I'm actually looking for very explicit mathematical. I kind of get the general idea.
I will show you something.
Because of my lack of knowledge, I
will show you something like that.
Okay, we can have a chat about that maybe.
Yeah.
Yes, we can check.
I think at this moment, he is more focusing on your Hadamard space, then you consider a bunch of operators of various types.
Yes.
Then you do this asymptotic analysis of this bunch of operators and other properties. That's what you do. I mean, that's not has anything to do at this moment with nonlinear differential equations.
Yes, for now, they are not, he doesn't know where they are going, but he's just saying they might want to consider that. And the name of the mapping they are constricting is what they call, let me see, asymptotically regular enriched map. It has been defined somewhere else. So it's like, maybe it's defined in form of norm.
Yeah.
Now they want to bring it in form of a metric space now.
Yeah.
Now they have to look at how can we write it, and before they can be sure that this is working well in Hadamard space, they need to put some things. Like I said, I think it should be a result one time like that. They've proved that it is closed, convex, and so on. So I think they have like 4 things.
Great. Yeah. Thank you very much.
Thank you very much.
Thank you. It was nice talk.
Was never.
That's normal.
The second part in links, I just downloaded it inside. I just downloaded it. It's inside. Yes. So when the second part is
We also had actually a question from the chat here. Can you explain more about the interdisciplinary impact you mentioned in your significance of study? And I think you already answered there that you're not there yet, right? To be able to expand on that. What particular challenges do you anticipate in establishing the existence and uniqueness of fixed points in Hadamard spaces compared to other metric spaces? This question is from NC Tema. Thank you very much, NC, for the question. But you're probably kind of in the beginning of your studies. You're probably not yet in the position to maybe answer that, right? But thank you very much, NC, for the question. Could you maybe use the microphone if you don't mind? Yeah, thank you.
Yeah, thank you very much. Our second presenter is Mr. Thoriso. And then he's working on a new method for solving the variational unity project in real spaces. The supervisor is Dr. Janelidze and Mr. Prof. Over to you, Thoriso.
Good afternoon. My name is Thoriso. I'll be discussing with you my research, which is involving solving variational inequality problems in real Hilbert spaces. So, this is the outline of my presentation today. This is the work I've already have started doing. I'm still yet to do the application part of the mathematics. So, but some of the results have been observed. So variational inequalities are general and powerful mathematical models which unify concepts in pure mathematics and also applied mathematics. These can include systems of nonlinear equations, which is very interesting. From when we start with linear equations, systems of linear equations. Now we're getting into nonlinear equations, and you know it's a where the also at least one of the equations is nonlinear, and we can get solutions to those equations, and also optimality conditions, looking for also minimization problems, optimization problems, getting the minimum, the maximum of functions. When we derive those functions and we key them to 0 to find where the minimum points and the maximum points are. And then it also goes into network equilibrium problems. So that's just the general optimize variational inequality problems can deal with. So this is the definition for a variational inequality. It's we have a set, a K, which is a subset of a real Hilbert space, where this set K is convex and is closed. And then we sorry about that. Oh, okay. Yes. Where we have our inner product and the norm respectively denoted as that, and then F being a Lipschitz continuous operator, which is also be understood as a mapping. So we consider of finding a point in the subset such that we have that equation over there. So this is called the variational inequality of Storm-Picture type, because he later introduced it into this. Introduced it, yes. So variational inequalities were introduced by Hartman and Stopaccia in the 60s as a tool for the study of differential equations, with applications mostly importantly drawn from mechanics. Initially, variational inequalities were infinite dimensional rather than finite, but the breakthrough for finite study occurred in the 80s. So literature has shown that this problem has been solved by projection type methods. For instance, I'll still get into them in the literature. The projected gradient method, the sub-gradient, extra gradient method, extra gradient method and the sub-gradient extra gradient method. So these are the projection methods we're going to be using to solve this variational inequality problem. So I've stated here that I'm interested in the same forward backward method for various reasons that I'll still get into in this presentation. So there are some research questions that we thought of, for this project. Can we construct, an algorithm that is faster? Also, my second point, computationally less expensive. Can we have an algorithm? Can we construct an algorithm which is very simple and elegant, or just, like not gonna be require much computation? So yes, and can we really apply this into some life existing problems? So I haven't really got into how the method we did or you were using can be applied, but we are still looking into it. So that's the aim of the research, was just to introduce, a new method to solve variational inequality problems in real Hilbert spaces. Objectives is to carry out a well-developed study of the concept of variational inequalities, and to carry out a study of the projection type methods also, and to answer the questions that we set out for ourselves. So yes, I'll just to split that slide. So in the past decades that have elapsed, there are a number of methods or algorithms that have been introduced to solve these variational inequality problems, of which the most well-known one is the projection gradient method. Also has been proved to converge this. Yes, is the first one is the projection gradient method. It's the most well-known one. So this one has been proved to converge if our function f is inversely strongly monotone or f is strongly pseudomonotone. So the challenge with this one was that if f is monotone, then the algorithm will not converge. So another researcher studied this problem using the extra gradient method. Yes, and now he was able to show that the sequence that we have the x is converges to an element set of which is the solution set of the functional inequality problem if f is monotone, which was a major breakthrough at that time, and but it also had certain limitations. So researchers also worked on this because it had most of the algorithms in the literature to solve variational inequalities governed by Lipschitz continuous and pseudomonotone operators. So with this exaggregate method, it has two projection operators. That PK there is a projection operator. So because it is computationally expensive, some researchers wanted to remove that one, and then another researcher came with an algorithm to decrease the number of computations of the projection operator onto the convex set. So we introduced the subgradient extra gradient method for this, and then the TN is a half space. So he extended the work that other researchers also did, and also was able to tackle the challenge of the computation of that projection operator. So I haven't put in the algorithm for things thanks forward backward method, but it's one of the algorithms that so I apologize for that one, but it's one of the algorithms that has gained to a lot of attraction from researchers because of its applicability. It uses only one projection operator on the convex set, and hence it's a better algorithm compared to what other researchers have done. Here are some basic notions, definitions that we use for our study. The operator, for conversions, we normally use we require an operator to be continuous, and so we have that which is continuous, but in some cases where we don't have the Lipschitz continuous constant, we can use a variable step size method for solving variational inequality problem. Yes, and some cases we show conversions on pseudo-monotone operators, and also my interest for further study in what I'm still going to study is study the strongly pseudo-monotone for a result with the method that I'll be using. I'm still using. Yes. So yes, that's the research methodology. The data collection.
I think you can skip
You can
this
skip
slide.
this part.
Yeah.
Yes, yes. I don't think it's
No, I meant just to skip that slide.
Oh, that one. Okay.
That one. I don't think that is very.
Yes.
useful for now, yeah.
That consideration. I don't think also, but
Yeah, also this one.
this one. Yeah.
Yeah.
These are the slides I was using for.
But maybe that one was interesting. The other one with the table of your schedule of what.
Oh, okay. So this is how I carried out some the research. You know, we studied the variational inequalities, in which spaces they can come into. We identified some gaps in the study, and now we want to see how fast the algorithm we constructed is compared to how fast can the rate of conversions is compared to other methods in literature. And worked on the proposal, and should be submitted to SMUREC, Sefako Health Science University Research. Yes, and we hope to complete. I hope to complete my master's with the research. Still going. Like I said, there's only just the application parts to the how we apply this into the real life existing problems. So unfortunately, I don't have much information on that. So thank you. These are the references.
You maybe leave this slide on the list of references while we're discussing the questions. Thank you.
Okay.
Maybe what we can do, you can give a summary, maybe 2-5 sentences for what are you gonna do? What is existing? What will be your contribution?
Okay. So there's what I'm doing, right? And what is existing and what is my contribution. Okay. There's a method we constructed using the thanks forward backward method. It's a forward backward method. So he's the one who introduced it. So normally I just call it a Zing method to solve functional inequalities. That is the one that already existed. So there are some further extensions of that method that generalize to the classical backward method, like the inertia. The researchers who study inertia properties that so these properties help to speed up the rate of convergence. So right now what I'm doing is that I'm studying the correction terms, and just to see how fast also the rate of conversion is compared to I study the correction terms with the inertia and Zeng method, because of Zeng method has an advantage of it is computationally less expensive. Hence, and also with the addition of the correction terms and the initial conditions, to see how fast the algorithm is to in solving for in the rate of conversions. So that is the contribution that I've added into this problem.
Any question?
This is a master's project, right?
Yes, sir.
And so when did you start? Are you starting now or?
I've started around May, so I do have some results. I just haven't looked into its application in terms of into the reward applications. But I have done the mathematics theory part. Yes, so still having to complete a paper with the algorithm that choose everyone into solving the variational inequality problem. And then we will see how it also compares to other methods in terms of how quickly it converges to the point in the set of the variational. Yes, so I'm still going to further see how it can be applied into real life cases. So let me go back to the first slide just to say something interesting. Okay, it's not here. These models, mathematical models, can also be, traffic network systems. Can be now using drivers can now use these models to choose the routes that are the cost less for them. So also it's something that you could look into. So also game networks.
So is this something that you've studied, those applications of the existing work? Have you thoroughly studied how the applications work, or is it something that you've just read that it's possible to apply there?
I haven't studied, I just read about it.
The definition of variational inequality. Yes, yes. Okay. If you are ready to change your religion from analysis to algebra, then processing approach would be interesting. You take a subset of Aphane, and then you take a map from that subset to I, that's to equals L. And then you just take a vector space, not inverse space. You can define the inner product from a vector space. And this whole expression will make sense what you wrote there.
Yes.
And it could be interesting to understand algebraically without this inverse space structure.
Yes.
How much mathematics can be captured from there? What structurally these things actually helps us? Does it make sense? So you replace your H.
Yes.
Just by a vector.
Okay.
Take final
Yes.
condition for the sake of simplicity. Okay?
Okay.
You can always endow inner product in a vector space. You don't need any topology anything.
Yes, yes, yes.
I'm generalizing it slightly in the sense that you take your F from subset of Rn to Rn. So instead of real valued Hilbert space, now you are taking Rn to Rn. Okay?
Yes.
Then this whole expression, what you wrote as number one, absolutely makes sense.
Yes.
In this more general setup, what I'm talking about.
Okay, yes.
It could be interesting that how much mathematics structurally you can capture this general setup. And
Yes.
that can also tell you that where exactly you need this kind of structure from function analysis.
Yes.
But
Yes.
what I'm talking about is pure algebra in some sense.
Sorry, Amartya, how is it what you're saying more general? You seem to be specializing to a specific Hilbert space, no?
No, not Hilbert space.
Rn.
Rn. I'm just taking
What is
R,
R?
real number.
But Rn is a specific kind of a Hilbert space.
Yeah, but I'm not taking. No, he's working on real Hilbert space. I'm taking Rn.
But isn't Rn a special example of a real Hilbert space?
So he's taking values in R. Am I right?
With regards to the space that I'm dealing with and how it can, can move this problem into the more general algebraic which is the Rn one. There have been some cases where it has been studied into but for which I think generally does look seem to be more easy to understand on the algebraic sense, but for a more for it to be more applicable, it's where we use the real Hilbert space.
I think what Professor Zurab is trying to say is, if it is still Rn, it still remains the same. Because in fact, the problem was defined in Rn before they move it to Hilbert space. So it's still the same thing. Nothing happens. So if I'm still taking my F from a finite dimensional to Rn, it's still called the variation inequality problem. But I don't know if there will be if there's an algebraic something for that kind of stuff. But for me, variation inequality problem was defined in finite dimensional space, RS. So before people start moving it to some general spaces. So yeah, it will still retain its same thing, like still variation inequality.
But the Prof's question was, if you're moving from R to R, then Rn to Ra, if I understood you.
Oh, no, but Prof said if that H is Rn, which we know that it's still
It's a special case.
It's a special case, so it still retains the same property, it's still conventional.
No, I'm not using Hilbert space structure of Rn. I'm just considering vector space structure of Rn.
But we need we need inner product to describe the inequality, right?
But isn't it somewhere you are also using some topology here?
No.
Yeah, but with vector space, I think there are some things that I've seen somewhere.
By the same way, this can be extended to the other parts.
Yes, that would be nice because. I don't know, I mean, of course, we need to check whether you can send some.
Yeah.
Yes, and
Any other question? Okay. In the absence of question, we can thank this. Our text is very sad. It's Bafana, talk about the computational exploration of anti-diabetic drugs using the reverse degrade into original indices and the QSPR modeling. The supervisor is Mr. Fatlane, and Bafana, over to you. You have to tell us what is QSPR modeling. Over to you. Thank you.
Afternoon, everyone. Prof has already indicated, the name is there. Supervisor is right there, for sure. So, yes, this is my research topic, computational exploration of anti-diabetic drugs we are using QSPR modeling. So, now I want you to picture this in your minds right now, right? Imagine imagine a world whereby you can test or design or discover drugs without even being in a laboratory or not even using a single test tube. Does it make sense? Sounds like fiction, sounds like mystery. But even myself, I thought for a second, am I willing to even pursue this kind of a study? So I later found out that yes, it's possible for you to design drugs without even being in a lab and without even being a pharmacist. Now, what I would like to tell you is that my research will be strictly on diabetes, as for sure. You already know. Okay, yes.
You can just press on the screen once and then it will work.
Okay, this is the structure of my presentation, as you can tell from the introduction up until to the sources. So beginning with my introduction, it has been reported by the World Health Organization that every year, approximately about 1.5 million deaths occur as a result of diabetes, and millions and millions of people are getting infected with this. And as you know, diabetes is a chronic metabolic disease that is characterized by persistently elevated levels of blood glucose in the blood as a result of the body when it cannot produce or efficiently use the insulin it produces. So with the passage of time, this disease will lead to severe damages to essential organs such as the kidneys and everything. So by just mentioning this, we can tell that there's a need for us to come and try to help and discover certain drugs that will help us fight and manage this deadly disease. Up to today, there's no known cure, but with ongoing rapid innovations in mathematics, technology, there are researches that aim to help and find suitable molecules or drugs that will help us to discover some of the drugs. So in my paper, there are certain drugs that we chose particularly from a previous paper that has been worked upon, but using a different perspective. In that paper, they used classical degree-based topological indices. And as you have seen in my research topic, I'm focusing on reverse, not classical, right? Okay, so as we can go forward, now, these are the drugs that have been studied by the previous researchers. So we will be continuing on their footprint. So now, what is graph theory? So graph theory is a branch of mathematics and computer science that that deals with that studies and deals with applications and properties of graphs. And graphs are structures that are used to find a relationship between two objects. I can give an example. You see, as we were taking a tour in the campus, you can classify this campus as a graph whereby the buildings are connected together. We are using the roads. It's more like just to give an example of a graph could be anything, and I just indicated to you. So now, if I may proceed. So now, to be precise, under graph theory, my study is under chemical graph theory, which is important in drug discovery and development. So in our study, we are going to be with the drugs that I've already mentioned. We will be studying their properties, physical properties and chemical properties to find suitable molecules that can help us in determining which molecule is best for treatment in this study. So now, if I may continue. So as I've already indicated that we've got different types of graphs in different fields, and graph theory not only does it focus on pharmacy or pharmaceutical research, but it is broadly used in other fields such as data science, computer science, and so forth. So right now, if I may, okay, a second, please. So as now, yeah. So in particular to applications of graphs in chemistry, when we talk about or before I can explain this, so how do we represent drugs as graphs? Because now our focus is on drugs. So a drug as a graph will be given, as you all know, we have got carbons and hydrogens and other atoms in a certain molecular compound. So what happens is that any bond that you see in a molecule is represented as an edge, and the symbols, what you call the elements, I can even use can I interpret? Okay. Just to continue, let me give you a brief example of how a drug would look like. And and the camera is, I hope.
I think you need to expand on that, Kishan, if you want to see what's happening there. Do you want to see if they can see or not?
Yeah.
Expand on that tab. Are you not okay? Look at them. Yeah. Yeah. And now we can switch the camera.
I can proceed. Okay, for sure, if you can see here, this is a structure of Aphane, right? From organic chemistry. I don't know if it's been. So now with us in graphs, we will represent this structure mathematically, just like this. And you may ask why there are certain changes. So now, as I explained to you, any bond in a molecule or compound is represented as an edge, right? So the question is now, now let's focus on the edges. We'll come to this one's the vertices. Now, as you can see, there's a double bond between two carbons, isn't it? So now when we represent them as graphs, any triple bond or double bond, we represent it as a single edge in graph theory. So hence why you see these ones. And when it comes to our atoms in graphs, we normally don't consider the hydrogens as vertices. That's why you don't see them here. We take note of different atoms such as carbons, could be oxygen, such atoms, right? So now this would be my vertices. Our carbons in this case will be our vertices. Now in graphs, each vertex has a certain degree. What do we mean a degree? A degree is the number of edges incident to that vertex. So if one may ask right now, this vertex has degree of 1 because there's only one edge that is incident to it. Does it make sense?
Are we adding more edges there, those lines you've shown? Is it part of the picture?
Where?
These lines.
Oh, no, I'm just explaining to you now. If there is.
So they're not, okay.
Yes, yes. So I just wanted to give you a representation in your head so that you should not be confused as to how we maneuver around. Is it fine?
So whether it's a double bond or single doesn't matter.
No, as to any multi bonds, yes, we just represent them as a single bond.
You don't consider multiple age.
Like
You don't consider multiple ages between C to C if you have more than one bonding.
Yes, yes.
You don't.
Yes.
You do.
If instance, these are multiple, right?
Yes, it should be.
When we represent them,
it has valency 4, so 1, 1, and there should be 2. Yes, I completely understand.
You understand it?
Yes, yes, of course.
Yes, yes.
But
So
you said that you replaced it by only one age, not 2 ages.
yes.
That's very strange.
Yes, but that's how they do it in graph theory.
No, that can be graph theory interpretation, but practically what you are saying, this chemical compound, whether you have a double bonding or you have a single bonding, doesn't matter.
Yes.
But isn't it very strange that a chemical compound, how it compares?
I think there could have been studies so forth behind as to why they would classify any double or triple or as one. I asked myself that question, but I couldn't dive more into it because it's not part of my.
I think the reason we're using only single bond is because in our research we are specifically focusing on simple graphs. So they have to
No, if you do mathematics, I have no problem. But when you are saying I'm doing applications, then I have a serious problem. That's my problem. Because this is a real thing. This chemical compound is
I think the point here is that is irrelevant. The shape of the graph is more relevant than the bonding.
No.
Bondings are probably determined by the actual atoms.
No. One also depends on you whether you have a double bond or not, because that is very much different. If you do a simplification as a mathematics model, as a simple graph, yes, I completely understand. Then you can study. But when you are saying I'm solving it's a real problem, then how these approximation methods does not affect back when you go back to the real world?
I think they do apply because remember, as I told you, not only does it being utilized.
Maybe
Okay.
let's give him
Yes.
chance
Yes.
to
Yeah,
let him continue with the
you finish your
presentation.
Oh.
And then when you finish, and then we can now engage. Maybe
Engage.
as you present, we will be able to understand some of the
Yes, as far as I've seen also in the literature, right?
Literature means it's a paper written by a mathematician or it can be a scientist.
Yes.
There's a very big difference between who writes the paper.
That's why I'm saying.
Yeah, let him finish, let him finish. first.
That,
Then-
and then you will.
Then you finish, yeah.
You will get. That is not really. You present what you know to us, and then we will continue the engagement. Sounds interesting.
Slides are shared already, you don't have to reshare, yeah.
With regard to this is yeah. So
Maybe switched off or battery is gone.
yeah.
Yes.
I think we can still leave it here.
One, two, 1, 2.
Maybe try speaking louder.
Yeah.
It's a useful skill to have, so.
So now, in particular to applications of graphs in chemistry and pharmacology, they are founded on the topology of chemical graphs. So to determine the topology of a chemical graph or this graph of chemicals, we introduce something called a index of a graph index or a molecular describe. So a topological index is a numerical value that is obtained from the structure of the graph, representing a molecule which is invariant to the graph isomorphism. So now, topological entities have important tools for investigating between many physical, chemical, physical and chemical properties of molecules without having to perform them physically so we have different types of topological indices which are classified according to their spectral size and so forth. So now, if I may continue, okay, so actually now discussed the development and application of quantitative functional relationships, which are QSPR. So a QSPR, because as we define it, it may not make sense. So I'll briefly explain it. So let's say you have a group of molecules with similar properties such as boiling points and toxicity and other properties. So if you take these properties and then you want to check their similarities and so forth. So you will then do what you would describe them using what we call topological indices, right? And then after doing that, you will use machine learning or statistical models to link the property of interest, let's say boiling point and the other, so that we can see which molecule is used in which. You understand? Makes sense, bro. So now that's what we talk about QSPR models. So in this paper, like I've said, we have computed degree-based topological indices and the reverse degree-based topological indices for antibiotic drugs. So the concept of reverse vertex degree was introduced by and the importance of reverse degree-based indices is that they provide complementary structure information to improving model accuracy by capturing patterns in molecular types. So now you can ask yourself, like, why did I choose reverse vertex, reverse degree-based topological indices, especially in relation to anti-diabetic drugs? Is that when we checked, me and my supervisor, we've realized that there has been not significant or enough study when it comes to reverse degree-based topological indices. If they are unexplored. So we want to research and find out what if they have a more efficient use than the classical ones. So if I may so the aim of this is to study the reverse topological indices and try to use them to predict physical and chemical properties of our cell graphs. So this would be achieved through the following objectives. So we are going to compute degree-based topological indices of the all molecules that we are focusing on, and then that's why we computed the classical ones. So after that, we are going to develop the QSPR models, linking these indices to the properties that I've already mentioned when I was explaining the model. After that, we want to evaluate the predictive performance of these differential indices in relation to the classical ones, which have already been studied or researched upon. Meaning that we want to see if the mass could be more efficient if we could use them in future. So now, hence we're talking about forecasting ability of the health. So these are some of the research questions we asked ourselves. Can reverse degree based on this is accurately describe the molecular structures of new antigen drugs, and how strongly do this synthesis relate to physical, physicochemical properties and biological characteristics in our PSPR modeling, and do reverse indices provide benefits or additional perspectives in comparison to the traditional indices. So now we are on to the significance of the study. This one even goes without saying. We just, if I may sum it up, we just want to see if we can use reverse degree for anti-diabetic drugs in the future. Just to sum it up. Continue to our literature review. So as I was trying to explain what a graph looks like there. So a graph is a set. It's a set that is composed of a set of vertices and edges, right? So as I indicated that the edges are typically chemical bonds and the atoms are the vertices, right? So the degree of a vertex is the number of vertices adjacent to it. As I was telling you that time, like they were the number of edges incident. So, and each edge connects one or more vertices, representing the interactions between atoms, which are bonds. So to facilitate the prediction of physicochemical properties of these drugs, the TIs, so the topological indices have been developed, as I explained earlier. So like I've told you that there are different types of topological indices which are classified according to different categories. But the first degree based topological index was introduced by Millen in 1975, and it's because the equation of that topological is given there, and it's part of the ones we computed or computed in our paper. There are many more. People we use, I think 9, which 9 of them. For presentation purposes, I couldn't control it. So the second one is known as the KTC, which is the atom bond conductivity index, and the equation is given as that. So, because we've been talking about the reverse degree based token, so the concept of reverse latex degree and capacity, and the equation is given as follows, but forgive me, there's an error. See here, there's supposed to be +1 here. So it's just an error. So in that equation, when you see delta G, that one represents the highest degree in a graph. And then the second one will represent the degree of that vertex, the certain vertex in the graph. So based on previous publications, one of them in 2024, Nagesh and others, they tried and introduced reverse-based topological indices to cancer drugs, and upon their findings, they found out that the reverse topological indices were highly correlated physical properties of the pathway investigated. This means that whatever the TIs, the reverse TIs, means in future, they will be used when we try to compute new molecules to anything. So this is another previous literature. So if you don't have a question for COVID-19, and should I continue? Should just escape here. In this one, you just can skip this one, this one as well. This one. These are my references, and yeah, thank you for listening and paying attention.
Is this time for questions?
Questions.
Are you familiar with the work of Professor Fatlane and Simon Mongwe from WITS, Farah is from UJ. They do very similar work applying graphs to drug discovery. And they recently have come up with a drug that worked kind of on mice. They now want to patent it and then start trials with humans. Are you aware of that work?
But I don't know of both of them.
You don't know both?
I know both of them.
You know both of them?
Yes.
Are you?
One is at WITS.
Yes.
Yeah.
So one is at WITS and
Yeah,
one is in the.
Yeah, I know.
Are they in the municipality?
It's one by PhD graduate. It's also by PhD and by research, mathematical biology. So they did together because of this combination, theoretic applications to mathematical biology.
So in terms of our focus area, what you're doing would fall nicely under Eric's project. Remember, I showed you Eric is counting subgraphs.
Yes.
That is very close to to these topics, because these invariants could be linked with the kind of invariants that Eric studies. So that there is definitely a potential connection there.
That is exactly why I was asking for the slides.
Right, and I'm gonna
saw something.
send it now. Sorry, I forgot. Yeah.
Any questions?
How do you define the topology of graphs?
And of the topology, it introduces what you call topological elements.
Yeah, you said topology. Topology in a mathematical sense, or it's a different meaning?
As in fraction.
Like a topological space, what I was talking on the board.
No.
No. That's so.
Okay, and this is still an honors project, by the way. Yes, so we can thank the speaker if there are no questions.
Yeah, I will attack you later on.
No problem, Prof.
Okay, you wait for the attack.
No problem.
Thank you very much. Thank you so much.
I was actually expecting that.
We can check if there are online questions.
Oh, yes, let's check that.
No, there are no online questions.
There are no-
They're shown on the chat if there were.
We're introducing, I'm going to the.
We have to look.
You assist to it.
Yeah, it's the presentation is there.
You see those references?
Yes.
None of them is medicine journals. None of them in medicine journals. And then what you write against this. Mathematics journals. Do you see my problem?
Probably something already gives nice result, but then I give you that you start introducing.
Yeah, I mean, you were telling me this whole chemistry is nonsense. Whether I guess that doesn't matter.
I'm saying this is a simpler approximation that
Yes.
maybe is already working a bit.
So simpler
Then
approximation.
of course.
So we focus on the connection of it. On carbons, not the whether there's a connection between them.
But my remark is that we shouldn't look at what they have done in the literature till now. We have a better idea again.
The new the member is psychology and it presents evidence-based proximity finding results from what's M-matrix spaces. It's being supervised by Professor Nai Salim and supervised by Professor Maggie Master Group. Greetings to you all. My name is Malose Mokonyama, and I'll be presenting about the title called Coincidence-Based Proximity for that on Palestine space. Then this is my coursework outline structure. So somebody can ask what is a fixed point. So a fixed point is when you take a certain number as you substitute or you compute in a certain function, then it will give you a certain that number. I can give you example by taking a piece of paper and put it inside the photocopy machine. If you take the piece of paper and then you put it inside the machine, that paper will still remain the same. And then if you frequently repeated it, that paper will still remain the same. So that unchanged point, we call it a fixed point. Right? So a fixed point
a fixed point is a basic foundation in an important tool in nonlinear analysis, general topology, functional analysis, and geometry, because fixed point theory can be used to solve a various problems in mathematics, engineering, and computer science. So the most important about the fixed point theorem is that it can provide the existence and the uniqueness of the problem solution. So there are many various applications of a fixed point theorem, such as solving chemical equation, testing the algorithm, and modeling the genetics. So the concept of the fixed point theorem was formally introduced by the Stefani Banach in 1892, between 1892 and 1945. So, formally introduced by the Stefani Banach, which is known as the Banach theorem or so he formally explained using a metric spaces and set metric where is it that a point P is not at a point if equation 1 and equation 2 are satisfied. And this is an example of the example of a theorem. So this example called for a theorem. And then you also try to explain a contraction mapping using a metric space and a self-mapping. Where is it that a mapping G is known as a contraction mapping if there exists a constant which ranging between the interval of 0 and 1, such that equation 3 is satisfied. So also come along with the theorem says that explain one using the complete metric space and the self-mapping be a contraction. Then G has a unique fixed point theorem if equation 4 holds. However, the Banach fixed point theorem is restricted to a self-mapping. In the scenario of involving non-self-mapping, a fixed point theorem may not exist. Hence, the equation 6 may not have a solution. So, this limitation, it motivates the development of the best proximity point. So, the best proximity point extend or generalize the concept of the fixed point to a non-self-mapping, where equation 7 may not have a solution. So, hence, a best proximity point seeks to identify the possible solutions by minimizing the distance error, which is given by equation 5. So, I can give you a real life problem about the best proximity point. So, let's assume that a student to pass the module must write an Excel. This is a solution, right? So if that student cannot, or this may not be able to write the exam, what best proximity point will do is that will suggest a student a possible date for him or for her to come and write that test. So that makes absolutely makes sense. So yeah, it will minimize that issue of writing by this equation which is given by equation 5. So mathematical, a best proximity point is defined using a two subset, which is an A and B. So a point P is called a best proximity point if equation 5 is satisfied. So since I spoke about the if the equation 7 does not hold for
So think that this A and B are equal from the third mapping, from a non-self mapping F, then the best proximity point will reduce it to a fixed point problem. Hence, the equation 6 and equation 7 has a unique solution. Then again, we have the concept called a coincident best proximity point. So a coincident best proximity point is the distance between a non-self mapping and a self mapping. So which has to satisfy the following the equation 7. So if it happens that this equation of starting with G is the identity mapping, then every coincident best proximity point become a best proximity point of the mapping time. Problem statement. The classical fixed point, the classical and best proximity point are well established in metric spaces. However, these classical theorems are not generally enough to be applied to a broader and more complex basis. Presently, Ayov and other researchers extended the M-metric space to quasi-M-metric space and established several fixed point results using a left gamma and right gamma consequences. So in 2021, Salem and other researchers extended the concept of the best proximity point theorem to a coincident best proximity theorem in a control type metric spaces. So this study seeks to investigate the best proximity theorem and the Banach contraction in the setting of quasi-M metric spaces and explore their application using the tools such as left and the right consequences. So this research aims to extend the best proximity point result to coincident best proximity result in the quasi-M metric space and define new concept related to result. And this study will address the following research question. If S, Gam is a quasi-M metric space with two non-empty sets A and B, where A and intersection B are empty, and F is a non-self mapping, can we define a best proximity point using a left and right gamma sequences? And then under what circumstances will left and gamma best proximity point become a best proximity point? And then can we find example of best proximity result in quasi-M metric spaces and some application of the best proximity result? So here the motivation, which I motivated by the work of the Salem and other researchers who extended the best proximity point result theory to the coincident best proximity point theory in the control type spaces using the two distinct mapping. And then I motivated again the extension of an M metric space to quasi-M space by Ayobi and other researchers, and then the finding their fixed point using the left and the right gamma consequences. And then this research aims to bridge the gap between fixed point theorem and the best proximity point in the quasi-M metric spaces. So research and aims. So my aim is to study the left gamma and the right gamma coincident best proximity point in the quasi-M metric spaces, and then also to establish some new results to apply some obtained results to some operator equation, and then to show how the best coincident proximity point result generalize the fixed point result. And then my objective is to explore and establish a best proximity point and coincident best proximity point theory in the quasi-M metric spaces, and to extend
some new concept and to provide some illustrative examples in the application of positive metric spaces. So significance of my study is that studying the best proximity point theory in quasi-metric space is a useful tool for addressing a real-life problem where a symmetry or balance and the exact solution may not exist. So for this, from this network system and logical artificial intelligence and the economy, this theory enables the decision makers to identify the closest possible solution that minimize the error, cause disagreement, making it higher valuable in the modern systems. So before I come here, I like to explain what is a metric. So a metric is a mathematical tool of determining the distance of the length between two sets. I can say between two.
Yeah, I think you can skip this, you all know. It's fine, we all get this.
Yeah. And then I just want to
Well, if we go back to the previous slide, Professor Goswami says we all know. But do we all know, for example, that the condition 1 can be deduced from the rest of the conditions? Who knows that? Do you know how to do that, Professor Goswami? How to deduce condition 1? It actually follows from the other axioms of metric space. Is this something you know or is something you don't know? First time I pointed this out to my lecturer who was teaching me metric space in my university, that condition 1 is actually a consequence of the other conditions. I will show it to you after your talk. How is it a consequence of the other conditions? So we don't have to require condition 1, we can prove it as a consequence.
Yeah, I think it start with 5. That's why you have the inequality, and then you take the point 10 somewhere.
Yeah, something like that. Yeah.
So should I just one or but my presenter will no longer make sense. No longer makes sense.
I assume you have presented this part. And then go to the next slide.
The reason why we're asking you to skip is because we all know that very well. We already assume you already told us about it because we know it very well.
Okay.
Okay. In 1994, a Matthews extended the concept of that metric spaces to and introduced a partial metric spaces, and where he allowed the non-self distance to be a non-zero. And then he developed some fixed point theory, and then he broke down some Banach contraction principle. So lately in 2014, Asani and other researchers extended that the notion of the partial metric spaces to a metric spaces. And then this is how he defined M metric spaces, that to be a space to be called a classic. We call M metric spaces must satisfy this condition, which is identity condition, and minimum self-distance, symmetry, and modified triangle inequality. And then he also observed that every metric space is an M metric space, but the converse does not hold. And then again, presently, Ayo and other researchers, they extended this space to quasi-M metric spaces, where they define a quasi-metric spaces to hold this for this condition, which is identity condition, minimum self-distance, and modified triangle. So it's been observed that every M metric space is a quasi-M metric space, but the converse does not hold because this one does not satisfy the symmetry condition, and then the minimum self-distance is not necessarily zero. So again, similarly, it's been observed that every metric space isn't quasi a metric space, but the convex does not hold. So here is the example of quasi-metric spaces which satisfy all the conditions of the quasi-metric spaces. So since the class of metric spaces is contained in the quasi-metric spaces, the notion of the convergent couch sequence completeness and some fixed point theorem are already exist. So my job is to extend the notion of the fixed point to a best proximity point. That is what I'm going to do.
Sorry, 9 and 10 are exactly the same, no?
Which one?
You repeated the same thing twice, or am I misreading something? What's the difference between your first, when you say define the function gamma by, and then you say after that, they seem to be exactly the same, no?
Yeah. I think
Okay, thanks.
So should I
Okay. Could you maybe leave on the list of references, if you don't mind? Thank you.
Thank you very much. Let's thank the speaker. Any question?
Oh. So what you are doing is you want to, for the space where you are working, the fixed point has already been established. Yes, we want to generalize, since you said the coincidence points. Yeah, like, I'm extending fixed point to best proximity point because of fixed point is dealing with the self-making while that one is dealing with the non-self-making. Okay, and for the other space that I said, the smaller ones, have they done the coincidence point at that for those spaces? Have they considered that? Since you are, you know what I'm trying to say, that you have metric, say you have M metric, quasi M metric, you are considering the quasi M metric. Now for the M metric now, is there anything like coincidence, best proximity, or what do you do? Have they done that there? Yeah. Okay, so you are just moving into that. Yes.
The first speaker was talking about special type of metric space, which was the Hadamard space, right? I mean, we have define a geodesics and the pixel structure. Does it make sense to generalize this Hadamard space to your either M metric space or quasi metric spaces?
I'm not familiar with this.
Yeah, I mean,
I
of
think
course.
it can.
I mean,
You can extend it.
because that could be nice understanding between not only collaboration, but also understanding what he is doing, how far it can be extended, because these are the extensions what you are doing there.
I think already there is something.
There is something,
If I'm not wrong, there's something.
some generalized Hadamard spaces by generalizing your metric spaces. Something. The question is how to find one equation 4. You give if you have a complete metric space and if it has a function, then you have a linear. Theorem. Yeah. Do we have any kind of necessary and sufficient conditions when we guarantee unique fixed point on a complete metric space? Yes. What is that? Can you repeat the question again? If I have a complete metric space, do we know any necessary and sufficient conditions for an existence of a unique fixed point? Because this is only one side. It has to be but if we are in that because it's probably complete metric space.
Yeah, what do you mean is maybe you stop this one.
Yeah, so if I have a complete metric space and I have a unique fixed point.
Yeah.
By some map. Does it imply the map will be construction?
Which map? Which maps?
The map will be made to fixed point.
Not self-making.
Any map which gives me a unique fixed point.
G. Yes.
Will G be contraction? I'm asking opposite question. Is this very known result for many years or?
No, of course it won't be a conception, but it's just unique fixed point. Why should it be? I mean,
Yeah, there is no.
I think it won't be.
Contraction, yeah. So I'm sure there should be some necessary and sufficient condition on a. The construction. Yeah, of specific type of map.
Construction principle, I think we would, construction. For this now, if we add some space on it, I think, it's just like half of the banner construction. Or down, not yours.
No, I'm saying, yes, I have a complete metric space, so I have a specific type of maps, say contraction. Then it says that you have a fixed point, unique fixed point. But can you characterize unique fixed points for a complete metric space for a given specific type of maps? Like, as Zurab said, the converse, there is no reason the converse should be a contraction map, but is there any class of maps for which on a complete metric space, it is a characterizations?
Yes, I think. There's some, I think it's a known, should be a known. Yes.
In the metric setting.
Yes. Yes, should be, yes.
In the metric setting. Maybe in other spaces, that's what can be investigated.
Yes, in a more general space.
Yes, in more general space.
Yeah,
Maybe
for
that's
example, your in metric space, quasi-metric space.
I think
can you
that can be a
characterize
very good question to investigate.
in a general metric
Yes.
space. Can you characterize this?
So what is the question again? I didn't quite understand. What do we want to characterize?
So imagine we have a, okay, Abass is saying that it is already known
Yes.
that we have a complete metric space. And for a given class of maps, types of maps, characterize these unique fixed points.
What do you mean when you say characterize?
In the sense that if, say, imagine that if I have a contraction map, then he says you have a unique fixed point. But the converse is not true, that if you have unique fixed point, map may not be contraction.
Okay.
So I'm saying for which classes of maps, it's both way.
So that's the.
I still don't understand how.
Of which properties do maps that only have a unique fixed point have? Like if you can characterize maps that have a unique fixed point.
By its unique fixed points.
Another way.
But,
Maybe start.
but isn't the whole point of fixed point theory that you always try to find new classes of maps for which fixed points are unique? So there isn't like a once-off answer telling you all the maps.
No, not all the maps. Do there exist a class of maps for which the unique fixed point is its characterization?
That question I don't understand. I don't think Luca understands that question either.
I think I do understand that.
Yeah.
Okay, I think we should take that one after.
Okay.
Because this one is not, let's thank the speaker. So there are no questions online.
Not online, no. So this is an honors project, right?
Yes, all of them. The masters were only two.
Okay.
So now there are six things for master project. No, it's the wrong.
Please. It's free.
We have been hearing about topology graph theory, and then now let's come to the applied very symmetric version and exact solutions of an option pricing equation for large equation. Our presenter is Tabello Monyebodi, and then the supervisor is Dr. Aphane. Tabello, you have to talk to us, tell us what is a mismatch, what is an exact solution, and the large agent over to Tabello. Yes, you are.
Thank you very much, Dr. for the introduction. Good afternoon, everyone. As my name is my name is Monyebodi, and my topic is mid-semester reduction of an option pricing for large ages. Supervised by Dr. Bafana from the Department of Mathematics and Applied Mathematics in SMU. So this is a brief outline of what my work entails. So now let's get right into it. So these symmetries are continuous transformation of the independent and independent variables such as scaling, right? So my definitions, I was supposed to put my certain definitions on my slide, but I can. But yeah, as I was saying, continuous transformation of the independent variables, such as scaling, that leaves the differential equation unchanged, right? So with that being said, I'll then get into, or rather try to bring an understanding as to Lie symmetries and the Black-Scholes, right? So the Black-Scholes equations have been studied by let me just restart. So the partial differential equations, they've been used in financial mathematics. They became a backbone rather of derivative pricing theory, which was introduced by Black-Scholes, right, in the early 1970s. So the classical Black-Scholes equation, right, as it is, it has limitation based on its assumptions, right? So this assumption is that they assume rather that financial markets are rather liquid, right? Meaning that participants, right, they are more of, they cannot, rather not more of anything, but they cannot influence the market, especially the I'm just volatility. No, I'm just okay. So
Relax.
Yeah, I'm just trying to. My problem is I think about a lot of things. Sorry about that. So, okay. They assume that participants cannot influence the market, right? And that they are more or less passive participants, right? So they cannot influence either the volatility. So especially when they are doing their hedging strategies. So these assumptions, they then brought forth what we know, the normal Black-Scholes equation, which is stated in the number 1, right? Where V is the option price, S is the underlying asset, T is the time to maturity, the sigma is the asset volatility, and then R is the interest rate, right? So although this model has been studied, right, it has more or less become less realistic in real life, right? Given the
the nature of the classical Black-Scholes equation. So, with that being said, most, especially a lot of financial techniques, right, in real life, they are what we refer to as liquid markets, right? So the Black-Scholes equation doesn't necessarily come and assist us a lot in that regard, right? So Jensen and Kepo then further studied this Black-Scholes equation, then extended on it. So in their model, then they introduced what we call a market effect factor, market impact factor, right? Which reflects the combined effect of hedges actions by large agents, right? So then we then have a new equation, a modified equation of the Black-Scholes equation with the introduction of the e raised to the power 2ADS, right? So if you look at that equation, if we then take our A as 0, we then go back to having our classical Black-Scholes equation, right? Which now this equation can now try to assist us in now the more realistic markets that we deal with in our everyday lives. So Ibrahimov and Garciso were amongst the first to apply the Lie symmetry method to the classical Black-Scholes equation, identifying its symmetry properties and obtaining exact solutions. Such reveals invariant properties that can be used to transform complex PDEs into much simpler ordinary differential equations, which now will enable us to try and solve these equations that we are currently dealing with, the Black-Scholes. Okay. So in this study, we are doing a review of the paper by Karakara, right? So the researcher investigated the nonlinear option pricing equation proposed by Johnson and Kepo using the model. The goal is to determine the viewpoint symmetry, construct an optimal one system of dimensional subalgebra, and then use this to obtain symmetry reduction and group invariant solutions. In particular, interest in giving solutions that satisfy the terminal payoff conditions of a European calls option and back option, where the 0 now would be the time at the expiry date. So the 0 is now the time at the end point of when now you are paying off the very called the payoff condition, right? And then now we have a new variable, which is K, which is now our prime rate. So in my literature review, what I'm trying to do so far, since what we are trying to do is learn basically how to do the Lie symmetries, right? So now I'm trying to speak more about PDEs. So the Black-Scholes equations, which was now developed, the Black-Scholes developed a PDE that could be used to calculate the price of European style options. So, which then assumed that the markets were liquid and that traders do not affect the asset prices. So this led to now the famous Black-Scholes equations, which I called it the classical Black-Scholes equation, which is linear and relatively easy to solve. However, these assumptions behind the model, such as no traction costs and infinite illiquidity, and the presence of only small traders can often are often unrealistic in actual financial market. So these limitations were the ones that I talked about earlier, that Kepo and Johnson's then came onto them and then tried to study them further, extending the equation into that equation, too, right? So moving forward, Gaziso and Ibrahimov then applied Lie symmetries to the group applied Lee group's theory to financial PDEs, including the classical Black-Scholes, showing that symmetry method can reduce PDEs into ordinary financial equations. These are the analytical methods. So various techniques have been used to solve the Black-Scholes equation and its nonlinear extensions. However, we are more focused on the Lie symmetry method. Lie symmetry, or Zan and others use Lie symmetry to find the Lie point symmetries of the Black-Scholes equation, constructed optimal one system of algebras to derive invariant solution. And then in the later stages, this was then extended and then identifying potential symmetries and calculating convoluted rows using diagram. So on the comparative studies, several studies have been examined, have examined the influence of derivative markets and large agents on asset prices. The impact of the derivative security markets on potential market manipulation was analyzed. Vitagic and Ma extended this by introducing a model where large agents influence function is defined directly on the price process of the underlying asset, unlike in the earlier models. So yeah, which uses the forward beta stochastic differential. So the aim of this study is to analyze nonlinear option pricing PDEs using Lie symmetry techniques in order to maintain reductions and accept analytical solutions relevant to illiquid financial markets. So research objectives. The objectives of this research, I place them in the number form. So firstly is to analyze the structure of an option pricing PDE derived by Johnson and Gepo, to apply Lie symmetry techniques to determine its symmetry group construction and optimal system of one-dimensional subalgebras, and show these symmetries enable systematic reductions, to show how the invariant solutions relate to practical financial scenarios, to validate them under standard boundary or terminal conditions. So now, when it comes to my research question, that how can Lie symmetry analysis be applied to linear modified Black-Scholes PDE introduced by Johnson and Gepo for modeling one factor term structure option pricing large agents, and in what ways can the classification of its optimal system of one-dimensional subalgebras lead to symmetry reduction and family of group invariant solutions? So my research methodology is as follows. We are applying Lie symmetry techniques to the nonlinear PDE of an option prices to determine the Lie algebra and construct an optimal system of one-dimensional subalgebras. Then we use the resulting symmetry generator to perform the reductions from PDEs to ODEs. And then we solve the reduced PDE analytically where possible, and possibly study their analytical behavior. Then this the biasness, the volatility, the consideration, then the time frame, the budget, and then references.
Thank you. Any question? The applied parts.
This is real application.
Yes, but it's taken from
this black shoals actually shows black eating diet, and there is another person called Nobel Prize in economics because of this work. And as we know, one cannot get Nobel Prize for the theory. You have to literally show it has been used. So this is a genuine applied.
Well, yes, and at the same time, there is so much mathematical structures that are hidden there. And Professor Abdul Kara, hopefully he will join us again tomorrow. He knows a lot of that.
Yeah.
It's called Lie symmetry. That concept leads to the notion of Lie algebra, which is something that in algebra people study. And of course, the groups are also involved there. It will be nice if you'd be interested to join in our focus area. It would be nice if you could explore this, also explore the structural aspects of the whole Lie symmetry theory, which, by the way, is very strong in South Africa. Lie symmetry theory is quite strong in South Africa, but mostly it's concerned with the equational side of things. Catching up on the structural side might be useful for the future of South Africa.
Okay, let's end the speakers. No session on that.
Oh, no. No questions online. I would see from the chat that were out.
Okay. Our last part one presenter is Mr. Pitso Tshepo. For sure, Prof is the one that referred to the feeling when you were.
Oh my God.
Just take.
The characterizing the molecular properties of antiretroviral therapy using the SOMBO indices. What is the SOMBO index? People come and share with us what is the SOMBO indices. Over to you.
Good day, everyone.
Good day.
So my research topic is characterizing the molecular properties of what are called characterizing the molecular properties of antiviral drugs using SOMBA indices. So I will explain further as we go along. My presentation, what are SOMBA indices? So first thing first, I'm also under graph theory, and I'll just give an overview of what a graph is, as my colleague already has outlined. So basically, under graph theory, we are studying connections or relationship between different objects. So a formal definition of a graph is that a graph is a pair consisting of an non-empty set of vertices and a set of edges. So in chemical graph theory, we represent atoms as vertices, and chemical bonds, we represent them as edges. So there are also other various applications of graph theory. They can be used in road networks, telecommunications. They have also been used outside chemistry, outside logistics and chemistry. They have also been used to model how diseases spread. So they've also been used in epidemiology. So the person who first pioneered this characterization of chemical structures as chemical graphs is Arthur Cayley in 1874. And then this paved the way for other researchers to come up with what are called topological indices, as my colleague has already outlined. So what are topological indices? So if we have a chemical structure, as my colleague has shown there, to model or characterize the physical properties of that chemical structure there, we use topological indices. So in my own research, can I quickly just go there to show? Okay, so yeah, this is a chemical graph here. So to characterize the properties of this graph here, we use topological indices. So it's a very efficient way to save up on costs and also time. We don't have to use experiments to characterize the molecular properties of this chemical structure here, or chemical graph as we call it under graph E. So there are various topological indices. The first one, it was coined or discovered by Harold Wiener in 1947, and he termed it the Wiener index. So basically he used it to characterize the chemical structures or chemical graphs for alkane molecules. So he discovered their boiling points and other physical properties of alkane molecules. And then there are other different topological indices as well. We have the Rendick index, which was introduced by Milan Rendick in 1975. We have the geometric arithmetic index. So just to move along, because I think my colleague under graph theory has already given you guys a background of what we do. So under my own research topic, I use Somba indices. So we have different classes of topological indices. We have what are called distance-based topological indices, and then we have neighborhood sum degree-based topological indices. The one that my colleague here is using, I didn't know that class of, you said it's reverse. Yeah, I didn't know about that one, so I also learned something from him today. So mine are degree-based topological indices. So if we have a chemical graph like this here, it's an atom, so we represent it as a vertex. This here is another atom, we represent it as a vertex. So this link here, or this chemical bond here, we represent it as an edge. So it means if this graph here, we can label it, this atom here, or this vertex, we can label it as vertex U, and then this one we can label it as vertex B. So it means both of this, and also the interesting question that Prof you raised, why do we use sample graphs? I also have to look into that, because I think there are other different ways to characterize these chemical graphs, but for our case, we characterize them as sample graphs. So we'll have to look into why do we specifically use sample graphs. So to characterize the chemical properties and physical properties of this, I use the Somba indices, which are degree-based. They fall under the class of degree-based topological indices. So like I said already, there are various classes of topological indices. We have distance-based. So if we have distance-based topological indices, it means if we have a chemical graph like this, we are going to use the distance between these vertices to characterize their physical properties. And if you are using a neighborhood sum topological indices, we are not going to use this, and then we are calculating, we are trying to characterize the physical properties for this vertex V here. If you are using the neighborhood sum degree topological index, we are not going to consider this one. We are going to consider the vertex U that is adjacent to this vertex V here. I don't know if I'm making sense. And if you are using the one that I'm using, which is degree-based topological indices, we are going to use the degrees of these vertices here. So this vertex U here, it has only 1 degree because a degree just means an edge. And then this vertex V here, it also has a degree 1, which is just this edge here. So I use Somba indices, and I use reduced Somba indices, and I use average Somba indices, which were, by the way, introduced by Aphane Gutman in 2021. There are other various variants of Somba indices. There are elliptic Somba indices. There are a lot of them, but I only focus on 3. And I use those Somba indices to characterize 16 antiviral drugs of HIV and AIDS. So yeah, just to give a brief overview here using this simple chemical graph here to characterize the chemical graph here. I'm going to show you exactly where I'm at, the current stage where I'm at in my own research. So we are going to say the Somba index of this chemical graph here. This is the equation we use. This is du squared plus dv squared. So this is du here, it represents the degree of edge u, and dv here represents the degree of edge v. So my du here is going to be 1, and my dv here is going to be 1 as well. So it's going to be the sum. This is the sum of those degrees. If I had other degrees here, I was going to include them, and then I sum up all the degrees that I have, and then I get the value here. Let's say the value that I get here is √2. So to determine exactly the relationship here between my topological index and my chemical graph here, researchers came up with what I call QSAR model and QSPR model. So QSPR model mean quantitative structure property relationship, and QSAR model means quantitative structure activity relationship. So we have QSPR model, and QSAR model. So this model here, this one, if we use it to characterize the properties of this, it's going to tell us the physical properties of this chemical graph here, and then this one here is going to tell us the biological activities of this chemical graph here. So the relationship between this value here and this, that's where I'm at. I'm trying to understand exactly, because we use these models to study the relationship between the topological indices of chemical graphs. So that is where I'm currently at my research. So I think I've given an overview of what is happening currently under the graph theory. And if you look at this slide here, there are other applications that have been done under graph theory. In 2024, last year, Yasin and his team, they investigated the efficacy of neighborhood degree-based topological indices of drug properties of HIV and AIDS. You see that they use the neighborhood degree-based topological indices. So I'm using degree-based, not the neighborhood degree-based, the topological indices that I'm using. And then my supervisor here last year, they completed the neighborhood degree-based of anti-tuberculosis drugs. They use the neighborhood degree-based topological indices. So yeah, I've already outlined the aim of my study, because the aim of my study is also to come up with a QSPR model, like I outlined there, to utilize the Somba indices, which are degree-based topological indices, to characterize antiviral drugs. I managed to assemble 16 of them: ritonavir, lopinavir, and others. 16 of them, and then yeah, why this study? So according to the Center for Strategic and International that is South Africa remains the epicenter of HIV and AIDS pandemic. So this study, we hope to help or contribute to the ongoing research to reduce or manage the epidemic of HIV and AIDS in our country. Thank you.
Yeah, any question, colleagues?
A very nice presentation. All presentations are very nice.
Okay, thank you.
So when you say that you want to, like, can you show just one example, or maybe just describe when you say that you're characterizing something? What does that mean? So also when you're at some point you said that you're establishing connections between the indices, right? Did you say something like that?
I was saying I'm establishing the connection between the topological indices, which is a numerical value.
Yeah.
Or it's a numerical descriptor of a chemical graph. So
So how does that look like? Like is it a table, or how does it look like?
The model.
The characterization.
The relationship or the characterization, yeah.
Yeah, I'm not exactly sure how the model is going to look like, but already I have the topological indices. I can just calculate it. I have the equation, so I can get the numerical value, the topological.
So you've got a collection of molecules.
Yes.
And then for each molecule, you compute those indices.
Yeah, and then now I'm trying to develop the model, because the model is going to tell me.
What does that mean? So I think that's the part I don't understand.
Yeah, the model is, I'm going to use that model to characterize. My supervisor still has to show me, after creating that model, after developing that model, how do you analyze that model so that you can tell, oh, okay, what are the physical properties of this chemical graphs? So we are going to use that model to characterize, as we say, the physical properties of those chemical graphs.
This thing that you call model, what is it? What kind of thing is it?
The QSPR model.
Yeah. What do you mean by model?
So what do I mean a model? So it basically, we use it as a to study that model. We use it to connect, I think, to connect the mathematics with the structure. So we are going to use that model, and then we can interpret that model, or we can. That model is basically analyzing the relationship between the mathematics and the structure. I don't know if I'm making sense.
Is it a system of equations, like a normal equation, differential equation?
The model, I'm not sure exactly how the model is going to look like.
But is it using machine learning, like he was saying?
Yeah, yeah. I think my supervisor, they were using machine learning to the models that they were using. I think they call them linear regression models.
Linear regression model.
Yeah, they were using.
Go back to that work from
statistical models.
Yes, that's good. Thank you. See, that's it. I think they employed QSPR model. They're using linear regression and machine learning. I think that's.
Yes.
Well, I don't know the structure, but I know they use all those.
You train the computer over a database.
Yes.
And try to understand whether your
actual
in topological index is related to some physical or biological.
Yes.
So basically, you compute the topological indices, right? And then there would be data coming from experimental data coming from the labs of the physical properties and chemical properties of those molecules. So what you want to do is you want to check which topological index can predict the one of the physical properties from there. So basically, you compare the data from the lab and the experimental data and I would say theoretical data, the one you just computed.
Okay, no further questions?
So the applications are like So
No.
we have our.
I think we're losing participants online.
Yeah, no, it's already late. It's already late. It's 6.
And it's actually only one.
You have to finish all of it.
I don't know if Musa is still, who is, wait, is Musa? No.
He was the one.
Finish all of it. You have to finish all of it.
What's the one?
He's the one.
Okay.
Who asked you, who posted your email address?
Oh.
This one. Could you please write your name there? Oh, you're sorry. No, I would like you to write your name, if you don't mind, yeah. By the way, is it all right if I upload these presentations and make it available from the website? Is it fine or is it secret to?
No, they just need to work on some tempo errors. I saw some tempo errors.
Okay.
Yeah, so if you can give them a chance to talk, let them correct.
Sure.
Nothing confidential things here, right?
There is nothing confidential. Or do you have anything confidential? If you have,
Yeah, please check all the typos and basics here and there, so.
Because it's gonna be blue card, first it test. Okay. Our last presenter for the day is the Sikelela Notununu. And then we'll be talking about symmetry reduction and effect solution of variable coefficients. Is it 2 by 1? Is it a,
Yes.
is it a 2 by
It's a 2 plus 1
dimension?
Yes.
And then you will finish. Equation. Over to you.
Good afternoon, everyone.
Is this number?
No, it's not good. You can never.
Oh, okay. Good afternoon, everyone. My name is Sikelela Notununu. And I'm doing my honors. Supervisor is Dr. KR, Aiden, and my research topic is symmetry reduction and solutions of a variable coefficient 2 plus 1 Zakharov Kuznetsov equation.
Are you okay, or do you need help?
Okay, so below is the outline of my research proposal. Unfortunately, my phone just broke. I thought I was going to use it, but now, yeah, I have to, yeah, be myself. So unfortunately, that we are all out of time, but I have to present because I'm here. So yeah, I'm going to present. As my topic says, symmetry reductions. It's the same thing as listening. One of my colleagues just came to present same thing, listening. I don't know if I have to re-explain what is a listening. But it's a listening is nothing but a continuous transformation of dependent and independent variables that leaves the differential equations unchanged, such as scaling. A scaling is nothing but the process of making differential equations and its conditions dimensionless. So we have complex physical processes such as fluid dynamics, plasma physics, and nonlinear propagation that are often described using nonlinear partial differential equations, which are PDE.
whereby a PDE is nothing but a mathematical expression involving an unknown function of two or more independent variables and their partial derivatives. Then these partial differential equations, they are essential tools for addressing problems involving multiple variables across various scientific and engineering fields, such as in finance. They are used for pricing and auction. And in mathematics, they focus more on a unique solution. PDEs, they are of different orders. We have first order PDEs, second order PDEs, and some are non-homogeneous and some are homogeneous. Hence, they are used in describing large data of physical systems. The history of the influence, they were discovered by Prof from 1822 to 1899. It developed the lead proof analysis in the late 1950s. So first we observed that his theory of the differential equation, it could be explained simply by means of his theory, which is based on the invariance of the differential equation, unlike continuous of Smith's. And we have other authors who started the new policy in speech are given. We have Stefani, we have Rumen, we have Ibrahimov. Then this is the representation of sophistry. To my problem statement, the generalized 2 + 1 ZK equation is just an equation that models the nonlinear development of ion acoustic waves in a magnetized plasma under the restriction of small wave amplitude with dissipation and strong magnetized field. And an ion acoustic wave is nothing but it's a plasma sound wave where the oscillations of ions and electrons the propagation of wave. Now, the ZK equation is given by, I think the equation will be this one. This one. Whereby A subscript 0 and B subscript 0 is nothing but the arbitrary constant. And Y, X, and C are dependent variables, and U is nothing but the independent variable, which describes the evolution of Fatlane and other constant waves in plasma. The aim of this research project is to obtain the Lippoin symmetries and its invariant solutions to of 2 + 1 Zakharov-Kuznetsov equation with time-dependent variable coefficient, and the objective is to find the Lippoin generators with time-dependent variable coefficient and its exact solution. And then exact solution, I don't know how to explain it, but I would say it's a precise solution. I don't know, maybe if I can write something, but for an example, if I'm given, let's say xy plus y, xy dx plus x dy is equal to 0. So then an exact solution will be if I differentiate this part with 1 instead of x. And then I differentiate the second part with respect to x now, instead of differentiating it with respect to y. Then if their answer is the same, then the solution we say it's exact. I don't know if I make sense. And then my literature review, I explained that the ZK equations
they will develop like Zakharov, called like the they describe the weakly nonlinear multiple dimensions solitary wave in magnetized plasma. And I explained this part. The ZK equation is nothing but multiple dimension generalized of KT equation, which was first derived, by the way, for describing weakly nonlinear ion positive waves in a strong magnetized lossless plasma in 2 dimensions. Here is my equation for KTV. Research methodology. In this research, we use the midpoint method to obtain the same reduction and giving line solution. I ask this schematic in error, which means all the values wrong by a certain amount. We'll then use the mathematical tools that will provide us with accurate results and validate them to avoid the unbiased outcomes.
You can pass this one.
You can pass this one, right? And then this one then is, and then there's my time frame, and then yes, my references. Thank you for your attention.
Any question? In the absence of questions, let's thank the speaker. I'm just telling it like for tomorrow. Just to give the audience, yeah. There's some ambition that they know what we have done.
Yes. Yes, I also.
Not necessarily.
First,
what should I be, what are you doing? What type of we are very good okay, happy. Yeah, tomorrow. Let's finish the rest of tonight. But let us prepare. Yes, prepare your presentation, even if it's one of your paper. Okay, let's talk later. And we are trying to. Prof, while the students were presenting, Dr. Abass, we were chatting. We wanted to request other colleagues who could not come so that they can present online, so that you guys, you have an idea of the areas that SMU has. So we try to engage 2 colleagues, Shafi and Mr. Ndofu, and then also Dr.
Yeah, PhD.
Yes, so we just wanted to check with them if they are available tomorrow just for an online presentation, so that if you people.
What about presentations from those who are here but who are staff members?
I'm also presenting.
You're present. Would like to present, okay? And what about yourselves?
I'll present something. I'm not sure if I can can present a slide. Yeah, I can cook some slide.
And yourself, Professor Aphane?
I'm not the.
So I'm just asking to
so
make a
that
planning. So tomorrow morning we have I think 2-hour slot for presentations in the morning. And then in the afternoon we have a hybrid presentation slot. This is when we will be engaging with other lead researchers from the focus area. They will actually be joining us tomorrow afternoon. Like Eric will be joining, and Serene will be joining, and Wenchi will be joining. So maybe we can schedule presentations from your colleagues in the morning session after the presentations but
After the
we'll have to see so that.
If it's possible.
Yeah, no, definitely it's possible. We just want to make sure that we don't violate the program too much, because now the whole of South Africa knows about the program and they're expecting to show up maybe online.
Okay.
But maybe we can over dinner make a plan and if necessary change also the program. So let's do like that. Let's finalize the plans over dinner, and then I'll update the program if it's necessary for us to change anything in the program, and then we'll be good.
Yeah. But anyway, the staff members that are left already we've got a taste of what we are working on. Is graph theory.
Absolutely, yeah. It was a very nice picture, yeah.
Yes, and also mathematics of finance.
Yeah.
So, Dr. Moutsinda, Siyabe is math of finance.
Yeah, it's mathematical finance, but mostly with the data science. Application in math of finance.
Yeah,
Yeah,
so
you see
those
that.
are the three left. So it's gonna be a duplicate of what you have yet today.
Sure.
Because the Shafi is
We have network now, Shafi is the network science.
on the yes.
So, yeah, so now, that's why I said, they just came back from India, they went to Dublin to present.
Yeah.
If it's possible tomorrow morning, I don't know.
Yeah.
And just two of them. Just put down. We have someone, I told you. We have
Let's look at that during dinner so that we
Yeah,
can
we-
schedule it in such a way that we are fitting with the schedule, and then if it's necessary, I will change the schedule also.
Maybe one who's different is the operational research student. We have one student and have the research. So if they push country start looking as a slot for hey, because it's something that is different. Yeah, but we will finish the rest. Okay.
But I think I should request for Amartya and myself to give very short feedback on the presentations.
No problem. No, yeah.
Before we close off.
No, before you close up, yes,
Yeah.
definitely, Prof.
Thank you.
Colleagues, students, thank you very much for the presentation. It is always nice to get a different perspective. It's always nice to be critiqued by experts. This is a learning curve. We are not ambushing you. All of us, we went through the same thing, but let us appreciate that the professors are here to give us a remark so that we can improve. If this is a learning curve to all of us. So I'm going to hand over to the two professors, and then you just give us your general remarks, and then feel free, Prof. Even after this, the remarks are still more than welcomed. Thank you.
Okay. There are two aspects of all these presentations. One is whatever you are currently doing, you pursue exactly in the same direction towards your masters. This is one perspective. The other perspective is there are lots of mathematical structures are embedded in your projects here and there, which not only you actually working on, even the experts in South Africa, they also don't work on. Like one is this Lie symmetries, what Professor Janelidze mentioned, because they're more interested on towards this solving equations in different contexts, whether it's an applications, cosmology, finance, mathematical biology, but there are lots of structural things, and whether you are working on graphs, even graphs, specifically you have lots of invariants. So this can be studied actually abstractly and try to understand the structure. So this is the structural aspect, which is our plan, I think, Zurab, tomorrow, right? To identify the structures and or on Friday. Structural.
Yes. No, there is very exciting times ahead.
So we wanted to try to understand the structures and extract from each of your things. So that's one thing. What my remarks is that let us, in case if you wanted to continue what you are doing for masters, then I have few suggestions for some people across the country whom you like to contact. Okay, because it's completely up to you, because what you wanted to do based on that. I forgot the first person I couldn't write his surname. You talked about this fixed point and Hadamard space, right? That's you.
Yes.
That's you, yeah. One of the very person who will be very interested about this argument is my colleague, Professor Rajendra Pant from UJ, because he works on fixed point theory and he uses some kind of structures on matrix spaces, but as far as I know, he does not work on Hadamard spaces, but it will be quite interesting if you contact him, in case if you wanted to pursue. Then the second speaker was M5, right? In the same. Please forgive me for my wrong pronunciation. Again, it's one of them will be Professor Pant from UJ. There is another person, Dr. Rahul Shukla from Walter Sishu University. He also works on fixed point theory, but he used fixed point theory quite a lot in other areas, not only just theoretical one. So that could be also for you. Then the third was Mabuza, right? Mabuza is absolutely Farai Niabatsa and Simon Mukwembe will be the very first people who you can actually approach. Of course, I mean, Fatlane can actually talk with their with them. Then Mokonyama, right? Your talk, of course, there are, I mean, Maggie is here and Sikuti is there. But apart from that, whatever I have listened talks from Agangi at Collins, at UNISA, and Ulela Otafutu at Limpopo University. These two people, I heard their talks in different conferences, and it seems to me there is a intersection what you are doing and what they are doing. Of course, not exact match, but possibly you like to contact. And then Monyebodi, of course, here is a problem. Lee symmetry is very strong in South Africa, and financial mathematics also there are people working. But the combination of using Lee symmetry method in financial mathematics, that number is very little. However, explicitly there is one person who is Kesh Govender from UKZN, who Kesh. Kesh actually works on Lee symmetry methods in different areas like cosmology, but also specifically on mathematical finance. So he could be an explicit person who could be contacted with respect to applications of asymmetry on financial market. But apart from that, of course, Parai Umshlanga at Limpopo University, he works on financial mathematics and that Bloch-Schulz equations, he works quite a lot on that. And then Jules Emba, he is at UJ. He was in our mathematics department, but he recently moved to the economics department of our UJ, and he literally works on this kind of thing. So, and he literally take the data from the share market and testing this kind of thing. So maybe you also contact him. And then, of course, Abdul Kara, the professor was sitting in the back. Of course, he works on Lie symmetry, but I do not know whether Abdul Kara do applications of Lie symmetry on the financial one. So, but we can check on the different aspects of it. And then, Tshepo, your thing again, Simon Mukwembe will be the best person, but Eric, what Professor Janelidze mentioned, Eric is using quite a lot of this invariant. And also my colleague, Peter Dunkelman at UJ, he also used some of these invariants, what you mentioned in your talk. So that could be the person you may like to contact. And finally, Notununu is again, Kesh will be very suitable person for with respect to finance and asymmetry. However, I believe there are some physicists as well at UKZN also use this asymmetry methods, because I think your equations come from physics, right? If I remember correctly, right? So there are some physicists, if I remember correctly, from UKZN who works on those areas of physics, but they use also Lie symmetry to solve, but I completely forgot. Yeah. Okay, so that's my feedback.
Before all these groups that you mentioned here, do they form, are they on the focusing?
Almost all of them. At least all of them are.
The answer is no. But I'm going to answer your question in my presentation. Yeah, in my. Most of them are not. Calendar isn't, for instance.
But they're NITEX associates.
Yes. But they're not working on mathematical structures.
No. This suggestion is not about mathematical structures. I am saying if they wanted to do what they are doing, then this is the suggestion. About the mathematical structure, that will be a complete separate solutions and separate treatment. I mean, that has nothing to do with this.
Yeah, but my question was, are they part of
Effects associate is.
Focus
No.
areas.
No, not
Other-
focus area, no.
Other focus areas.
Other focus,
Some of them are in
some of them are but not all. Like Farai Shlanga, yes. Jules Emba, yes. Farai Niabaza, yes. Olela Utafuga, I don't think so. And Eric is with us. Kesh is not. Abdul Kara, of course, is not yet. Yeah, half of them not actually.
Will Abdul Kara present it more?
Not really. We don't have any such.
But he will join.
He will be here.
Discussion.
Stop it. Okay, over to you. Zurab.
Okay, so first of all, I would like to say a big thank you to all the presenters. It was very nice. All the presentations were very nice. I was actually very impressed. And when you were saying that there's so many students interested in mathematics, it really sounds unbelievable because, as I told you, most universities in South Africa struggle to get students. But now that I saw the presentations of some of your students, it's just very, very impressive, and I'm so excited that you're all here. Then the second thing I want to tell you, I just posted on the WhatsApp group a publication on universityworldnews.com. A journalist reported on the NITEX inauguration last week, and there is an article on universityworldnews.com. And at the end of the article, the journalist, in his own way, described our focus area. And I want to read it to you what it says, because I think it's important for what we're going to achieve this week. This focus area advances ambitious theoretical work aimed at strengthening South Africa's scientific, technological, and economic progress. Led by Professor Zurab Janelidze at Stellenbosch University, the group brings together leading and emerging mathematicians around projects ranging from number theory and connectivity to graph analysis, mathematical models dealing with random or unpredictable events, and higher frameworks unifying algebra, topology, and logic. The aim is to break out of silos, Janelidze said. Mathematical structures should connect and unify knowledge across disciplines. End of the article. Of course, this is not a very accurate description of this story, but I think it's good enough. Now, the point is exactly that all the presentations that we heard today, all of them deal with topics which would be very easily embeddable in our focus area. And for each of them, the way forward, something that we skipped today, but maybe we will come back to tomorrow, but I just want to say a few more words about it. So those of you who are honors students and are going to be doing masters possibly next year, so what we can do is to have master's projects with you that of course involves your current supervisors, if they're still interested to continue working with you. But then you also get co-supervisors from various universities in South Africa. And large part of your master's project will be to take those core mathematical structures that you are already familiar with and to try to explore them in different disciplines within mathematics and maybe beyond. So that will actually be the goal of the master's project, instead of kind of building on some very specific problem that somebody in the literature specified 10 years ago, and then somebody else made some small progress generalizing it in this way, and then so kind of building on this narrow direction, which often is the thing that creates those silos, right? Instead of that, you take the mathematical structures that are involved in your current work, those things you already know, and then you'll be exploring the relevance and applications of these structures across disciplines. So you'll be strengthening your knowledge base, because this is masters after all. In masters, the main goal is for you to get a very good, deep and broad knowledge, right? You'll be strengthening your knowledge, but you'll also be kind of giving deeper roots in the specific area you're interested in. So if maybe in the PhD level, you want to come back and actually go back to those problems and develop it higher and higher, you can still do that. But then you'll have a very broad knowledge of where these structures that you use are also relevant in other disciplines. So we could actually create master projects for each of these that stem out of each of the honors presentations we heard that do that. With co-supervisors from various universities. I will be available for any of them. It's very exciting. All of these, even the financial mathematics one, which is far from me, but I'm very keen because actually the coordinator of the financial mathematics focus area, Messias Alfeus, he is also based at Stellenbosch, and him and I, we already had planned to start looking at mathematical structures that are relevant to finance and maybe getting a student to combine these two angles. Now, for the master presentations, those who are already working on a master project, yeah.
Before
yes.
Sorry for me. Before we started the leadership meeting, there was a proposal from the student. With what Prof. They were much more interested in the proposal was, what about if maybe next year, if possible, we found this side, we get people like him, then they can plan of the mathematics side. Maybe they can do for a month or 2 months, then look at that structure, connection, and then after that, then they go and pursue their masters. So that was the.
But when do they start masters?
Their masters is if they pass their honors
Yeah.
this year, then they can start their masters next year. But have a sort of like this classes with people like Prof. Amartya.
Yeah, of course. Yeah.
As like
You're not very far from each other, right? Johannesburg and SMU.
the
are
way
not
they
very far geographically.
enjoyed the connection, how it puts everything together. So if you make sort of like a program, a month or 2 months, they don't mind to come to this site. Get people like him, and then they know that after this, then they go back, they can pursue with their.
But what, that's a great.
I don't know whatever,
Yeah, that's-
what is it, we're gonna call it, a prof, and then who else will come in, because you showed my student the beauty of mathematics, and then you have to that.
That's a great suggestion, but what I'm trying to say is that we can already do that now after this workshop. We will be doing more of what he did in this week. And so we can already start making concrete plans as to what the master project should be, who the co-supervisors should be. Maybe some of them want to stay registered at SMU, maybe some of them want to move to another university. We can make all of these concrete plans at the end of this week. And then for the master presentations, so you can continue doing your masters, but if you'd like, and if your supervisors would like, and this doesn't even have to be an official co-supervisor relationship, you could embed in your master's thesis maybe one chapter that will be looking at those mathematical structures you're already studying in a bit broader way. Just one chapter there, and then after that, if you want to, then you can go further in that direction in your PhD, or maybe turn it in some completely different direction. So that will be my suggestion for the current master students, that we don't necessarily have official co-supervisor, but there is still maybe a chapter through the interaction focus area where they can go a bit broader. And this relationship will also enable us, because we're kind of we invested a lot of money for this workshop.
Yes.
And like I said before, to make real impact, we want to invest even more. So the idea is that with all these ideas that come up from this workshop, we will be able to pursue them and invite you every now and then to come to visit another university, or we come to your university, so we can take these discussions, the mathematical discussions, further. So that's my comment about possible way forward. But let's see what tomorrow will bring. Just a technical remark. So I now have new vouchers for us to eat. We don't eat the vouchers, we eat the food, but we use the vouchers to get the food. But there was a bit of a miscalculation. There is more of us than the number of vouchers. So instead of handing out vouchers one by one, that's what I propose we do, is that the vouchers you currently have, you try to use them again. If it runs out, I'll step in and I'll add another voucher to top it up. And let's see if we can save with this 1 or 2 vouchers, then we'll have enough number for us to then continue the same style. Otherwise, I can always kind of purchase together. Okay, so we all had to Nielsen.
Thank you very much for your kind words and all of you that you enjoy what I have to say. It's a great honor for me because I was thinking that